So very good morning to everyone. No, it was not audible. Good morning. So today's session, you already have the agenda, little bit tight, and we have too many of technical things. And except one or two sessions that you have heard yesterday, some of the questions are from that. The majority of the questions you will have the sessions from today. So do hear it. I am not giving presentation purposefully that you will note the key points from the presenter itself. And anyway, you have the guidelines, you can refer, and all other things you can refer. But we'll also discuss the kind of questions, what does it mean? So please focus on that. So you refer the agenda. Today, the first presentation is on data acquisition and handling. And the best person who can tell you about this, because he had created those platforms in APPC as well in many of the states. So you can ask, as weird question you can ask. You are free to do that. So ask the questions. You have any query related to your work, related to PCB or data acquisition system. He's the best person to answer. So he is here to get screwed as well. And he's going to tell you first how these things work. So over to Sudish.
Thanks everyone. Good morning. I hope you had a nice session yesterday, and hopefully this will be a little bit more enlightening as such. Again, I created a few slides primarily to ensure that I can share some of the knowledge and things which I've learned it over the last few years. So right from 2013 when I started the company, it has been always working on the Cems systems in India, working with most of the pollution boards, working with the CPCB and so on. And then I think we gradually looked at best practices across the world and how we can bring some of those in the country as such. So that's with that, I think I'll not waste most of your times around it. The agenda was around few topics. I think I wanted to just give you a gist of what happens in the whole country with respect to data handling and acquisition, and some of this comes from some of the key topics which I put it here. Again, we might not be able to go through all of those today, but at least try to delve to some of these topics as we go on. I also know that you might have attended so many sessions, so some of the basic stuff I am not really focusing around. I'm looking at some of the advanced topics which are required, the new regulations which has come in, and how compliance can actually help all of us in making a better tomorrow. So from a topic perspective, so some of the things which we look at it, the Cems guidelines was published in what have been discussed yesterday with respect to what CPCB expects from the guidelines perspective. And there are few things which I wanted to bring it down. I have summarized some of the points, especially from the data handling perspective, and maybe we cover that in one of the slides associated to it. But one of the important thing which I always realized that the enforcement has been a little limited is around the ability to verify the calibration of the system itself, the ability to check the authenticity of the data which is coming around and so on. But the guidelines clearly says what you need to do. You need to do a zero check on a daily basis at 10 o'clock. On Friday you need to do a span check and so on. But I find hardly a few industries doing this, and so it is some of the things, especially in the guidelines which exist, which needs to be enforced to make sure that the system is much more robust going forward around it. So from a guidelines perspective, we'll cover some of those, but I think this is one important thing right at the offset where everybody has to realize that a system of spending so much money building a whole SEM system is not very effective if there is no check put in place to verify that the authenticity of the data which is coming is accurate and enforceable. So that's something which I think all of us sitting here should really look at and take back, especially given I've been told that there are a lot of PCB officials here, so, and as well the industry, so it would help around from there on. The second process is CPCB has a very strict approval process on how the industry gets onboarded, how the process of getting the data submitted and so on. There's a lot of steps associated to it, and they have been refining this process over the period of time. And one of the most important change which they recently brought in is that to enable the industry to be accountable for submitting the documents associated to it. Earlier, the accountability resided with the vendor or the third party to submit documents on your behalf to the government. And now I think the fundamental change has been brought it is to make sure that it's the owners of the industry who has to ensure that the document is submitted. And when you submit that document, it is basically you are trying to certify yourself that my instrument which I have bought is primarily qualified and certified and basically performing to the best of your knowledge. Because today, that's one of the biggest challenge, and I think most of the sessions today focuses around how the accuracy of the data from the instrument makes more sense. But now, CPCB putting back one of the important thing back to you guys to say that yes, now industry has to ensure the instrument which you have bought and we have deployed is something which you are agreeing to it and you are submitting the documents associated to it. So I think it's one of the important steps associated to that. Apart from that, the CPCB asks weekly reports to be submitted. There's the inspections which were done prior to COVID. I think that was much more effective. With the COVID, I think that died down and the enforcements came down a little bit around it. Apart from that, I think the alerting system, the purple alerts, the orange alerts was a very important decision which came in from CPCB as well. So those were also some of the good regulations which were put in, where early warning indications were given to the industries to say, now you are on a purple alert, you are on a red alert, you are on an orange alert. So depending upon the gravity of the situation, the alerts are changing, and it's more important from that perspective. Similarly, I think everybody is aware of the Cems portal. Yes, there are challenges technologically on the portal associated to it, but more or less, I think the system has been in some form operational for the last few years, and I think it's a commendable opportunity there around it. So I'll talk about remote calibration, normalization, and so on associated to this whole thing. So the topic will cover around some of these aspects of it, but before going to the details associated to it, maybe we should look at how the state was there prior to all this regulation came into place and where we today exist from a open infrastructure for collecting the data from every system's perspective. So traditionally what happened is, in fact, I think as the country we should be proud about it, because I've been visiting almost many of the countries across the world, and I still see that they are still on the old model of system where there is a factory, there is a small system sitting there, somebody is sitting and monitoring the systems there and providing regulatory reports. We have moved much beyond that, where we are no more limited to the factory. We bring in through an open API, we bring it to the cloud, we submit to the data. There is a real-time visibility across the whole regulatory chain. And I think we have to take pride in doing that, because I think when I looked at across the country, we are one of the pioneers in doing that, and maybe one of the only country who is actually enforcing something like that, where a regulator sitting in his office can actually see the data of the plant in real time. You go to US, it's not possible. You go to any other place, it's not there. Because there is a lot more restriction on those implementation and so on. So I think as a country, we need to take pride in doing that there is a system which we have brought in, and it's our responsibility to make sure this is one of the best in the world as such. So from what is the benefit of this is, any instrument, any make can transmit the data. There is no proprietary systems in place. This is operating on an open system as such. And in fact, CPCB has gone to the next level now, trying to build an open system itself, where every industry can transmit the data directly irrespective of whom you are working with. So that's the new system which is implementing or is on the works as such. So from a country's perspective, I think this is one of the big achievement for all of us, and I think we all deserve credits for bringing that into the life. So this is kind of the typical schematics on how data comes to life. So you have the industry, you have the instrument which you have put in through. So as part of the instruments, there are certain instruments which are primarily analog, old instruments which gives 4 to 20, primarily not recommended in the newer world as such. But yeah, there are older instruments which still tries to give you the 4 to 20. So then in that case, there is a converter associated. but otherwise it's mostly direct data from the instrument coming in, coming to a data logger as such. Earlier it was a PC-based system. CPCB started enforcing, making sure that it's a data logging-based system, primarily to avoid tampering, making sure that it's not easy to make changes to the instrument. That's primarily the goal associated to it, bringing a data logging system in place. And then the regulation says that from there you need to transmit to the government in two different ways. One, you should use either a GSM SIM or a GPRS SIM or with an Ethernet-based connection. So earlier, they were very strict that no, you need to have broadband, you need to have a static IP and so on. But I think people have realized that that's not something enforceable, and the regulation now has been made it more broader, that it's about connectivity to the government associated to it, and also giving you multiple channels of communication as such. So which is one thing which is again very good around. So when the data comes in, it goes to SPCB server, because the state boards has their own regulations and servers associated, and then the data goes to the vendor server on the cloud. From there, it goes to RTDMS portal, which is there. And this is what the government is now trying to eliminate, is primarily the vendor server in between, so that industry can directly push to CPCB as well. But yeah, that will take a little more time. But yeah, that's on the works right now. And then from there, I think we get SMS, email alerts. Everybody can see the data in real time. You can see it on the state boards. You can see it on the CPCB server. So this is kind of the system which is today enforced and enforceable in the country right now. So this was, I just wanted to bring to you that, yeah, there are still traditional systems sitting there where people try to do most of their manipulation on the data on the PC. So I think there is a regulation to move to a particular data logger or IoT-based systems. They are more efficient, especially from when you go to carbon accounting and figure out, okay, now I need to calculate a carbon footprint, and even Cems systems carbon footprint, it's a huge itself to contribute to the whole system itself. So IoT-based systems are lightweight, in the maybe power consumptions, as well as tamper-proof. Those are the things which are in place for that. Similarly, traditional systems were primarily on-premise servers which were there. Now most of the data is now moving to the cloud, so that's another good change associated to it. Earlier, CPCB was also insisting on physical server. Gradually, everybody has now been open and accepting cloud associated to this whole data transmission. So I try to create one simple schematic to show you how usually the data transmission happens and how it comes in. So from an architectural perspective, if you look at it, there are many stations associated to it. There are different stations, each connecting to a single data logger or multiple data logger, depending upon the nearness to the stations. And based on that, it comes directly to the CPCB. Sometimes it goes to a central server and goes from there. But yeah, the expectation is that from each of the data loggers, the data goes directly to the pollution code. So that's kind of the expectation. So now once data comes in, what really happens? Once the data comes in, then there are kind of a lot of data analytics which needs to happen through. And some of this work is done by the pollution board, some of the work is done by industry. But yeah, there are quite a bit of reports which needs to be focused around and look from there. So I see that there are ideally 4 items we need to look at. One is data availability. The guideline says that you need to have 80%, 85% of data availability which needs to be enforced to. So that's the guidelines in India, at least, to say that you need to ensure that the data availability of all your systems should be more than 85% to be at least compliant to. So then the data quality is the next aspect of it, to make sure that you are transmitting data in real time and not delayed. So there is delayed data is not really acceptable or considered acceptable around it. It's only acceptable to some level when the internet is down, or there is a cost to justify the delayed data as such. But otherwise, the expectation is data is transmitted in real time to the board as such. And that's kind of where one of the element is the quality of the data. Now the quality of data can come in from different segments. One is whether the instrument is within the calibration range to give you a quality data. So that's going to be one of the criteria associated to it. Whether there are certain issues with respect to spikes in electronic signals which are coming. So there is a regulation associated to that. Is any spikes which are of sub-second duration or less than a minute duration can be eliminated as part of the data handling and acquisition system. So some of this has to be actually brought in as part of the software to make sure that you are not getting penalized for exceedance which you don't really have caused it. It was more of an electronic spike which has come through, and it should not be treated as a failure as such. Apart from that, data gaps is another area which usually the pollution boards usually monitor, and it's basically an indication to say that is the industry shutting it down, the system, just because there is an exceedance at that point of time. So understanding the data gaps is something which usually is looked at, and that data gap is actually going back to the availability aspect of it as well. Similarly, there are many other analyses which are done, especially on correlations, looking at from a startup and shutdown, because obviously emission levels will be higher during startup and shutdown, and how those can be counterbalanced as part of the whole analysis. So there are reports which we provide in that lines. Sometimes there is analyzer drifts which are there, how using data you can figure out. So those are reports which are actually created out of the Cems system from a reporting and analysis perspective. So these are kind of some of the ways the analysis is done with respect to understanding the quality of the data, the analysis of the data. So you could basically plot all the data, look at from a data quality perspective, these are the different data quality codes which are there. Then looking at what thresholds or limits have been put in place and how the system is exceeding those limits. So identifying those. So this is some of the basic thing which everybody does from the system perspective. But there is this ability to do a little bit more advanced duration analysis, primarily to look at how the system is performing during day and night. Is there an impact because of the whole pollution during day and night? Because there are certain systems which you have seen that there is a night, there is a heavy pollution coming out either because of the production going up or because of somebody not governing it, somebody not controlling it. So you could basically look at analysis on that perspective and stuff like that. You can actually look at from a day of the week perspective, maybe weekends, there's no operations, you would see the pollution going down. On the weekdays, it will come up. So from a regulator perspective, this is also a good indication to understand whether when the factory is operating, not operating, how is the pollution really looking at, and is there any insights which you can derive from there on. So looking at a calendar view of that information is another important to look at. Especially we did some analysis during the lower production time and the higher production time, and you can see how the data quality and the exceedance are showing up. So these are some of the informations which will help you look at from overall perspective. So these are some typical reports which I try to bring it out. The other one which is very, very important is the early warning system. So mostly creating, saying that, yeah, if this is how the data is going to come through, so what is the forecasted data going to come in the next 6 hours, 10 hours? So this is giving an early warning indicator to the industry itself that if you operate under the current situation, this is where the exceedance is going to come through and you are going to fall around it. So many of the industries in India has adopted to some of these systems to say, give me an early warning alert so that I can inform my operator to take corrective action before it becomes a exceedance and before a notice gets issued associated with it. So these are systems which are there, and I think it's some of the interesting aspects of how to do data analysis and being able to do forecasting associated to that. So now, since I've covered the architecture aspect of it, then I looked at some of the reporting and analytics aspect of it. Obviously, it's a rush through to give you every glimpse of what it is. But from a regulation perspective, I try to capture some from the guidelines itself. I actually yanked some of the contents from the guideline itself to tell you that from a data acquisition perspective, what are the guidelines which needs to be enforced to. So from obviously, they are all expecting that the data is transmitted in an encrypted form and it's tamper-proof. That's primarily everybody's expectation associated to that. The second most important thing is to make sure that the system is open, everybody is able to send the data, there is no blocking of information from anybody, so that's another other important thing. It was strange to see that the regulation actually modified from a 15-minute average to a 30-minute average. So that's kind of where it is showing up on the regulations as well. So in the guidelines is at least you need to have a 30-minute average in the Cems guidelines which is there. But ideally it was 15 minutes earlier associated to that. Apart from that, yes, there is the broad guidelines on showing that data quality is important and it has to be transmitted along with the data whenever you are transmitting the data as such. So those are some of the key information from there on. The second part which I talked about earlier was about the daily calibration checks which are required. So health of the instrument to be checked at 10 a.m. to ensure that there is zero drift. So basically passing a zero gas, verifying that there is no zero drift at 10 a.m. daily is a expectation from the guideline itself. Similarly, on a Friday at fix again 10 a.m. You are expected to do a zero and span drift checks associated to that. So those are the two important things. If you could do that and then try to calibrate the system or being able to measure the system against the calibrations, it will really help you the performance of the system itself. Similarly, if you look at the data capture rate to be more than 85% is the guidelines put in place from there on. The last point of which is they're saying that most of the people use zero air or basically the instrument air to basically do the zero calibration. So instrument air is not an acceptable zero calibration mechanism, and it's expected that you have a zero span gas created associated to that, which is a calibrated gas which is coming from those. So usually people use N2 nitrogen gas to actually do a zero calibration associated to that. So some of those are primarily the guidelines which is there from there on. Apart from that, there are certain guidelines associated to how the operating norms are calculated around to say that when you can consider the system is down and how you look at from the daily average calculations and looking from an averaging perspective. So those are things which are there, which you need to also look from. Again, one of the important thing is the instantaneous elevated data, which is the spike. So any software which you use in should actually curtail to that spike and remove that spike from the system so that unnecessary exceedances are not reported for exceedances which are less than 1 minute. So that's another expectation from the software to be handled around it. Then monitoring of the system should be done 24 hours. Some of the industries we have seen that they shut it down at 6 o'clock, factory shuts down, and the whole monitoring system is shut down. So as per regulation, it's not supposed to be done. Even if the factory is running, not running, it doesn't matter. The data monitoring system should be on, and it has to continuously transmit to the government associated to that. So that's kind of it. Then again, obviously, the plant startup and shutdown time of 30 minutes is also a leeway which is given for everybody. So that's something which most of the people don't utilize it. So that's something which we should look at. And then finally, the data transmission mechanism to make sure that you are able to do both GPRS-based data transmission and so on. So that's something I think which is also important to look from. So this is just to give you how the spike elimination model is basically built into it. So if you, this I have done it on a 15-minute average, but yeah, you can do it on a 30-minute average and see it. The impact of spike on how the exceedance will actually change. If you don't eliminate the spike, the average level values will go up significantly, and hence it will be reported as an average over the 15-minute or 30 minutes calculation which is happening around it. But if you eliminate those spikes, then I think the system will really give you a better quality of information. This was another information which I wanted to bring into it, is about the multi-fuel cases where in a refinery where you are using multi-fuel to operate some of your equipments, then the limits are dynamic, it's no more static. The thresholds or exceedance are not fixed. You basically have a leeway based on the fuel density which is used and the calorific value associated to the fuel. The limits are accordingly decided depending upon what type of fuel you are using it through. So implementing a dynamic, if you are using dynamic fuel, it is important to have a dynamic fuel limits calculated as part of the system. And again, some of the important things how we as a country has done much better than anybody else in the system. So this is basically a system to show how we basically do a remote calibration check. Because one of the regulation which says is that, yeah, the regulator should be able to sit in his office and being able to verify that the instrument is performing when we pass a zero gas and a span gas, which is associated to that. So a system or a control system should be put in place, which will ensure that you are able to shut down the sampling system and being able to pass the zero and span gas and check whether the instrument is reading properly or not. So a system, something like this is usually put in place. There are different models of the analyzer technologies, I think, which the rest of the sessions are covering it. And for each of these systems, the calibration or the check process is slightly different, and different processes are employed. So this is more for an extractive system, how do you do it? Then for an in situ system, how do you do it? But for all the systems, the fundamental thing is to look at whether when you pass a zero gas, is the instrument reading zero? If you pass a span gas, is it reading the span limits? That's primarily, it should be checked, and it should be checked by the regulator sitting in his office and not being able to visit associated to the plant. Some of the other things is, as part of the regulator, lot more anomaly detections are done, standard deviation checks are done. And see, these are some of the things which we do as part of our software to identify issues and so on. So there's a calibration done, then the drift associated to that, looking at calibration issues. These are some of the things which we constantly do around. Sometimes the quality of the data is an impact where absurd data gets transmitted and so on. So some of the checks are done, especially some people don't use analyzer, and data correlation is something which is enforced and so on. So these are some of the things which is there from a data analytics perspective, and maybe this is something which is important. We have seen some instrument suppliers actually do data simulation. When the instrument doesn't work, they actually try to simulate the data and send it. So it's when you simulate something like this really comes up. So you can actually watch for some of those as well. Yeah, so these are kind of a different analysis of the data which is there, and I just wanted to make sure that I give you time to ask some questions. But yeah, the overall topic, I covered 3 aspects of it. One is what is the general guidelines around CPCB for data transmission. The second most important thing is around what is the architecture involved into it, what are the complexity involved into this architecture, and third, obviously, the data analysis and what needs to be looked at from a regulator, what needs to be looked at from the industry perspective. So that's kind of what I wanted to end this session with. I think I'll leave it open to questions.
Questions?
Good morning, sir. As myself, Ravi Motwani from Adani. Actually, we are using your software, G-Lens software. That Swan is maintaining that one. But actually, sometimes we are facing some problem like that. Sometimes data is not available. We are not getting that alerts, and sometimes data will be high. So that is facilities available through SMS or something?
Yeah, so it's already, SMS and email alerts are already sent for all non-availability. In fact, there is a check which happens every hour associated to it, and alert actually gets in. So if you are not getting an alert, maybe the SMS is not configured properly or the emails are not there. So if we can meet out after this, maybe I can set that out for you.
Okay, sir. Thank you.
So any of the operational things we can discuss outside. I'll be there till maybe 4 o'clock today. So if there is anything, you can meet me around there and we can discuss. Yeah, go ahead.
Sir, for submitting the data, you told them ISO format is there. So the instruments are having some specifications on TUV and MSATs, means SOX, NOx measuring, like that. For the hardware, DAS hardware is having any specifications standardized by the CPCB or other parties?
So basically, one of the important aspect for the specification has been only that it has to transmit over an open protocol. So that's one specification has been put in place. The second specification, internationally there are specifications associated to how the DAS validation has to be done, because one of the critical aspects of the whole system is around the DAS system should be validated system. So especially in the European regulations, it's around MCERT certification of the DAS software itself has to be done around it to make sure that the quality of the handling. So because there are too many calculations happening inside the software, is the calculation accurate as per the standards? That's the validation which is there. Now transmitting the data, there is 2 or 3 formats which are there. The ISO format, ISO 7168 is the format for international data exchange associated to it, but it's not always mandatory across the board right now, primarily because there are some limitations with the ISO format with respect to handling the PEMS data itself or the Cems data itself. So it's not really always enforced around it, but yeah, it's a general guidelines to make sure that it is not proprietary. The idea was of ISO 17168 was to make sure everybody refers to a standard, everybody transmits the data as per standard, so that nobody can say that, yeah, this is my software versus their software. So the idea of ISO was to make sure that there is an open format of data associated to it. So as of now, from the country's perspective, the only thing is make sure that it's not tamper-proof. That's the only guideline which has been put in place. The second, obviously, is to make sure it is conforming to the open standards which are required from there. And the third part, which I would say, is to make sure that the software is a validated software.
Good morning, sir. Night presentation. And my doubt is calibration check, remote calibration check you told. How far it is accurate, sir? Generally, samples should be done at the plant itself, zero gas and span gas. You are doing remotely. So, I think...
Yeah, let me explain you what it is. So first of all, there was always a confusion around what the regulator is supposed to do. The regulator is not supposed to calibrate, so it's not remote calibration. First we need to all understand, it's not remote calibration, it is only check. So let's say you are sending data to the regulator. Now he is seeing the value of 30. How do you know that the 30 is actually 30? So to make sure that the regulator needs a control to say that I want to check. So he will push a button and say, let me pass 0. What is the instrument reading? Okay, it should read 0. When I span, the instrument should give me span. So this is the principle on which the remote calibration check has been designed by CPCB. To say that sitting in my office, I should be able to check the data which I am getting is right or not. And for that, they has enforced it. So how we do that essentially is, so there is a, see, if you look at from any, let's talk a simple case of an extractive system. So in an extractive system, you are taking the sample, passing through the sample conditioning and then giving to the instrument. So instead of passing the sample, you are cutting that sample and saying that, okay, you keep 2 cylinders, one with the zero gas and the one with the span. Maybe you can have a calibrator associated to that to dilute and give the concentration, but ideally the expectation is don't do any of those, just keep 2 calibration, one span gas, one zero gas, and let the CPCB control the opening and shutting out of that valve. That's basically what is remote calibration check. Now, for extractive, it is very simple. In situ, it becomes a little complicated, and that's primarily the thing. So that's where I gave you 3 models of calibrations which are there for different types of analyzers. For different types, you need to do it differently. But the principle remains the same. How do regulator validate that if I'm getting 30, is it 30 or not? And for that is what the check is all about.
Okay, sir.
Good morning, sir. What is the cost implication with respect to traditional and this online method? Like, what is the cost involved in this?
Cost from the whole system
Yes,
perspective?
sir, system
versus-
part. Only system perspective only. System
So
and
again,
software.
system goes in from different technologies, different ways to look at it. There are quite a range of process parameters, depends upon the parameters which you want to monitor, depending upon the software which you deploy around it. The cost is quite varied. I cannot give you maybe in this forum as what the cost range will be, but depends upon the instrument, the cost range would vary around.
Can an SME can afford this or not?
So, yeah, so that's a very interesting system to look at. Whether it is affordable or not, it depends upon how, see, every business has a business model associated to it. So, if you say not affordable versus affordable, it's a different problem because let's say the cost of producing something increases because you are putting an instrument. Everybody, once it is enforced, everybody is at the same playing field, correct? The cost of the product goes up. So I see it that way, rather than saying that whether it's affordable or not. Because for example, a sugar industry, the main concern comes in is from the sugar industry saying, okay, can a Cems system be deployed in a sugar industry which operates for a specific duration of time and will it? No, it's a market dynamics and economics. So first question is to see whether we want to comply to the guidelines. If you have to comply to guidelines, will everybody comply to guidelines? So then it's a level playing field for everybody. So then the cost of production is what is going up. So when you come from an economics perspective, that's how I see it. It's more about how we see the problem here is it's not a level playing field today. And that's the reason why you are coming with that question, because the regulator is not strict in enforcing the similar guidelines across the board. The moment you do that, this problem will not exist. The issue today is it's an uneven enforcement, and hence there is somebody who is at advantage, somebody who is at a disadvantage. So the expectation, again, sitting with all the regulators here, the first thing they all have to realize is I need to have an unbiased implementation approach across my place so that it becomes a level playing field for everybody. The system works from there on.
Yeah, good morning, sir. Here. We have a SPM monitor at my boy stock. We are facing a practical problem. Like, see, when we have reading, we are collecting the readings, and it is not reflecting on sometimes in our PCB server. When we are contacting my service provider, simply they are saying it is a server issue, PCB server issue. And after some time, they are doing, they may not doing even after 1 hour or 3 hours. Sometimes it is taking 8 hours time also. After 8 hours, again the readings are coming back. But whatever I have lost 8 hours or 9 hours reading in the server, I am unable to get it. But I have the local readings, which is recorded in my system. It is available.
See, there are two ways to solve the problem around it. One is every system will have its own challenges in one form or the other, and because it's a complex system, because there's an instrument, there's a logging system, then there is an internet, then there is a server, a receiving system there, a processing system on the PCB server itself. So there are multiple parties involved into this, multiple systems involved into it. So there are possibilities that there will be an error and stuff like that which is happening. But the best way to look at it is to understand the flow of information at different places and how do you validate and contact the right guys associated to it. For example, you said that, yeah, you are able to see the data locally very clearly, which essentially means the data local system is intact properly. So now the next point is whether the data is been taken from that system and pushed into the cloud or not. And that's the first thing which you need to see, whether your internet is up or not, whether there is a blocking of the system from there on. The second thing is then obviously you have to contact the server side and ask why certain information is not coming through. So there are two reasons why usually the server rejects the data, is some formats of that information is not coming up. For example, if you are sending a data to the live URL, there is a time window which the URL will accept the data. If the data transmission time and the receiving time is different, then it has to go through a delayed route. So the system will reject it. Now, understanding that at this industry level is something which is important. So for these kind of problems, I think maybe a more detailed session around walking through that whole process will be important. And maybe I'll request Sanjeev or somebody to arrange some of that session a little bit more detail to walk through the details a little bit more.
In the 99% of cases, we have checked internet connections in the factory level, but still we have a problems. And again, the most important question is here: who is the accountable for this, and who is the responsible for this deviation?
See,
Whether these NA recordings are considered as a deviation or not.
See, it depends upon when it is brought it up and whom is brought it up, and I am not the authority to decide who is the responsible person.
So,
but yeah, we
authority-
can take
Yeah,
that.
but yeah, you are also one of the service provider,
Oh,
so
no.
that's why I asked you.
This is a different platform. So the question which is coming from you is a genuine led answer. So who is responsible if the data is not coming, right? You are non-complying or you are not availing the data that much is required or 85%. Who is responsible? So, sir, who is responsible if data is not being sent?
See, for the PCB industry is responsible. The problem here is that, suppose take the example of Nara or Genus, whatever. I mean, these people are acting on both sides. That's not fair. Acting on both sides, not fair. You are working with the regulator, working the industry, that's not fair. Second thing, most important is that the so-called data acquisition system should be certified system. That is not happening in India. A lot of people are supplying data transmission system by saying that it was as per the regulations. Who are in the position to verify it? That's the major issue lies here. So my suggestion is that whomever is supplying the equipment, they have to equip to supply the software part also, certified software. Then only we can get the solution. Otherwise, it's pass on the blame game. People say that it's a problem is the server. Several people say it's a problem with the software part. That's the only solution. This so-called unlicensed suppliers has to come up with the certified software also to solve the problem. Thank you.
No personal question. Not your industry. You ask about the technical question and answer.
Sir, can't we have a VPN between the VPN, virtual private network, between the CPCB server and the participants? And can static IPs be given to the participants? To solve these issues like pinging and all, whether any network connectivities.
See,
Means from the server side problem or the participant problem.
see again, you are saying whether you can deploy a VPN or not,
Yes.
correct? See, it's a decision which the board has to take or the CPCB has to take associated to it. And till now that, because the problem with enforcing some VPN is around who is going to provide the VPN, who is going to manage the VPN. So that's the fundamental challenge associated to that. So from a technology perspective, I see VPN is much more secured from a data transmission perspective, and it should be allowed associated. But who is going to manage is the question, because if you provide a VPN from your side, will CPC be able to accept or state board will be able to accept? It's a difficult choice, because at their end, they cannot accept multiple VPNs. So they will have to have one VPN at there and give it to everybody, which means that the owners of VPN will write into the pollution board itself, which means that if there is any data issue which because of the security violation, it's PCB's responsibility after that. So that's the reason why it is not done. But from a technical perspective, I would say VPN is a much more ideal way to do this data transmission, and it's the right way to do it. But yeah, that's something, somebody has to take a decision on that.
When I look at Qual 1 certified data acquisition systems, one of the requirements is to have in the local data logger or in the first data concentrator, call it whatever it is, I have storage possibility for 1 or 2 days in case of data transmission to the cloud or the central server is not existing. And when data transmission is established again, then it automatically pushes the old data into the server, and this way no data is lost. Is that foreseen in the system here?
That's already implemented. It's not even 1 day. We basically have a 30-day window of where the data is stored locally, not 1 day, because sometimes the internet issues happen or something happens. The audit traceability of an encrypted data of 30 days is in the data logger all the handling system. So it's not 1-2 days, and it actually retransmits once the data comes through. So the problem should not, that's where I was saying, the problem should not exist. But yeah, that's a debatable point. So since that is a different thing, I know why they're asking that question, so I didn't go into that problem.
So we have already exceeded 15 to 20 minutes. So he'll be available during tea, lunch, till the 4 o'clock.
Yeah.
So keep asking. And we should move to the next presenter. So thank you very much, Sudesh. Thank you. Next presentation, as you see, is on Cems selection, PM and gestures. This is, we are not talking about what equipment you select. You have the guideline, it says all about it, the charts are given, matrix is given, and he is one of the known experts. He has been working on this and capacity building for a long time with us. Luckily, he is from some of the known supplier, but has never said that he is from supplier, and he doesn't talk about the brand even at once. I just note it sometimes if he has spoken that word. He doesn't. So he's a pure expert here, and he's not supposed to speak on what technology you have to select. This is your choice, guideline says all about it. But he's going to help you with something very important, is when you prepare the order, tender, what you should look for. What are the conditions that you should look for that you get the right product, or you can get the support after sales. Those are the required. So this is his presentation part, which is very important, and feel free to ask the question. Over to you, Shankar.
Yes, good morning everyone, and thank you Sanju for an introduction, because the total topic we are talking about Cems, specification, tendering, selection, after sales support. As asked, but you are asking a vendor to talk all these topics? What is this, right? The first question will all come to this mind. But since the vendors or the manufacturers have the challenges to give the right system, I think we can make certain topics and then we can discuss on this. So I will straightly start with the challenges. The most of the biggest challenges what we have will be multiple analyzers in one stack, right? There will be a flow, there will be temperature, pressure, there will be a dust measurement, and there will be a gas measurement, and sometimes different analyzers for various gas measurements. So there are multiple analyzers in one stack, how to do this. And then there are already multiple technologies which are available. What should I select? What should I put in the tender? How should we start specifying it? And then maintenance, availability, and the safety part of it. Today, safety is also a very important topic, right? Earlier, we had any caged ladder, and that was supposed to be the very safest way to access any platforms. But today, that itself is not sufficient, right? Today's safety is slightly more than that. And calibration, how to verify this remotely, and for us as an industry, how I can verify my readings, whether I'm generating the right readings or not as an industry. And also there is always an ever-changing emission limit values, right? Things are becoming stricter and stricter. We are moving towards more and more cleaner, right? Our industries are moving from an highly polluting to more and more clean emissions. Yeah, and everybody here can really see the difference, what it was 15 years back and what we have today. There is a huge difference. So things will be clean and clean only when the emission limit values keeps coming down and down. And when there is changing in the emission limit values, then there will be also change in the abatement techniques. What we used to earlier, sometimes we were using an ESP, today then we moved to an hybrid system, and then we moved to back filters, and then there were only certain ESPs. Now we are talking about an FGD or a DNOx, a lot of other topics and others what we are discussing, right? And this is also going to introduce new gases and other things. There could be more and more things that could come up. So this is the challenge what we have. Today we buy any system, select on a system, then how relevant that system is down the line in 5 years or down the line in 10 years, what is the life of the system and whether it is relevant or how I can be more able to use the system. Right? So what are all the steps? How to select in Cems? Step 1 is determine the process parameter as per the regulations, right? For every industry, there is a regulation. Let us go through it very clear. There are various components which are clearly mentioned with all the limit values and the measuring ranges, right? For an example, what it is given is for the thermal power plants. As we could see, the particulate matter 30 milligrams, sulfur dioxide is 100 milligrams, oxides of nitrogen is 100 milligram, and mercury is 0.03 milligram, right? This is how this looks like. When you take any standards, this is what it looks like. So what it means, how should I select a measuring range? So generally the measuring range has to be at least 1.5 times to 3 times of the emission limit value, right? You can be anywhere in between. Why 1.5 times to 3 times? Why not same as an emission limit value, or why not slightly more than that? Because we also have to measure some exceedances, right? When it happens, we should know whether it is exceeded by what value. So always that range has to be more than the limit values. And it cannot be very high ranges. We cannot make a range of 10 times the emission limit value. Let us say that we have an sulfur dioxide, right? 100 milligrams, and then let's assume that we have a range of 0 to 1000 milligram. And we know every accuracy of any instrument is always related to the highest measuring range. That is the calibrated range, right? Any instrument is calibrated for the highest measuring range. So your accuracy and everything will be for that, and for your smaller values, then you are in a big trouble because the accuracies are like that. So if you are still, let's say, emitting 90 milligrams, because of the accuracy, the analyzer might still show. It's a very good analyzer, but it is only calibrated for 0 to 1000. So it might show a plus or minus 10. So at 90 milligrams, you are still at 100 milligrams, right? So that is the reason that it is always recommended to have it between 1.5 times to 3 times of it. So that is where we could see here. For SO2, let's say that if it is 100 milligrams, then we do at 300 milligrams. But again, the topic comes with oxides of nitrogen. This we have to be very clear because of selecting it, the ranges, please select it as this is total NOx. This is not NO. When you get most of your NOx analyzers, you will get an NO analyzer, right? But when it is being reported, it has to be reported by multiplying it 1.53 so that it will be the equivalent NO2. So that is a reason that we will have to be very clear what it is requested and what we are going to specify. We will also specify NOx, okay, 0 to 300 milligram, you will get it, but then finally you will feel that this is not the right data. That is a very high value and you are going to report very high values. And there is one more this thing also you could see. Okay, why this moisture? There is nothing as a limit of moisture, and moisture is not a pollutant. Why should I specify moisture? Because the moisture plays a vital role in selection of the technology. Moisture is very good. Everybody want water, right? But any of this analysis, most of these are spectrometric analysis. And for that, moisture is always can be a spoil sport. So it is always better to mention what is the moisture, and it will also be good to measure the moisture so that we can report on a dry basis. And all this data are all on dry basis, right? It is not on wet basis, not on the actual condition. They are supposed to be reported on the dry basis. Compliance to standards. So this is something what you would see from the guideline, right? Every time acceptance of Cems until indigenous certification system is in place. So until then, either it has to be complying or following the US EPA performance specifications, or it has to follow the EN qual standards, right? So first we will have to understand as an industry what we want to ask. Most of the tenders we will say we want analyzer which are US EPA certified. And there are few analyzers catalogs which you will see that there will be an US EPA logo and then it will say it is US EPA certified. But everybody knows US EPA doesn't certify any emission analyzers. So when we ask, we will also have to be ready. If we want an US EPA compliant system, then we will also have to do the next steps. That is qualifying after the installation has to be done as per the performance specifications. That is also something that we will have to be very clear. Otherwise, when we go with the EN qual standards, that means they are already certified. You will get a certificate and you can also go to the web page and you can verify those certificates, right? And all relevant installation procedures to be followed, because every regulation has different, every certification has a different requirements, how to install it, right? So that also has to be followed. And for that we will have to be aware. And these are all publicly available data. There is nothing that it is only available with one vendor or it is available with only regulatory authority. No, this is a publicly available data. You can always enrich yourself with this data. And please be very clear, like when you specify what you would like to do. You would like to go with the US EPA or you would like to go with the EN. Specify it so that it becomes easier for you to compare and then buy and maintain the system. It is not only buy the system, right? You'll also have to maintain. And what I understood, finally the data industry is responsible. And this is a small comparison data which also you will find in the same guidelines. What is the main difference between Qual 1 and then US EPA topic, right? I'm not going more into it. If you have any questions, we can discuss later. And next comes the topic is about the operational conditions, right? I couldn't. Can you please play the video? It's a small video of an installation in a stack. Can you see this? This is in a stack, huh? It is not a process. And this is the sampling point. Can you see analyzer is mounted on the same level? Right. Why this video? Please specify your operating conditions. Don't specify design conditions. Design conditions either on this extreme or on the other extreme, and we will be never at the design condition extremes, right? We are more going to operate this plant at what level we are going to operate, at what is our normal operating. Please specify the operating conditions. Because of this, as you could see that instruments are mounted where the water is dripping. And we cannot change how you will operate the plant. We cannot change the process and other things. But mounting location we can change. We can change the technology which will be suitable for this. It is not that we will ask or any vendor will come and ask you or even pollution control board is going to ask you to change totally. But once you have already put an abatement system, then we should also know exactly where we can mount it and measure it without much interference. And with this installation, this will require regular maintenance. right? So to avoid that. And always consider future scenarios. We are not going to buy an instrument for next 3 years, right? It is not a mobile phone what today we buy, because after 3 years, no updates and other thing, we will have to change it. But same systems are not, we are not going to change in next 3 years. And already we are asking about affordability, right? So we cannot afford to change it at least in the next 5 years, 7 years. It has to run for at least 7 years. So please consider the scenarios, because you know about your industry, you know what is going to come, and you really know what is happening. Please be ready for that. Consider those scenarios. Example is wet FGD, right? Every power plant operator knows that if not today, tomorrow I will be installing a wet FGD. So we don't buy a Cems only for today and then tomorrow, okay, it doesn't work, we cannot change. Or you want to go for a dry FGD, right? Or we are going to go for a DeNOx. Yes, I have to reduce my NOx emissions after 3 years. If not today, there is no enforcement. That's what I hear. If not, but somewhere we know that we will have to come to this emission limit values. We might have to install a DeNOx, which might introduce ammonia as a gas, right? So then we be ready for that. So be informed, so that it becomes easier that you can discuss with any type of vendor, but then you can discuss and then say, this is my scenario. This is what my system, I expect this system to work for next 10 years. And these are all the scenarios we are expecting. And any additional components, right? Technology selection, I'm not going to do more on this topic, because this was one of the basic topics which we had discussed long back, right? So only thing is, check the preconditions to operate and maintain the Cems, where you have to install, whether you want an in situ, you want an extractive system, whether you will have a safe access to the platforms of where the in situ analyzers will be installed, or what it is. So those things you will be able to do that, and based on that you will select your technology. And also check if those technologies are installed in India and local conditions, right? Most of the things might have an international ones, but then their operating conditions and their operating fuel, everything could be totally different from what we are doing here. So this also, please let us make sure and ask whether this has a local references, whether it is locally working. And please evaluate worst case scenarios, which we have always seen. Because most of the time, we will end up in that worst case scenario for the instrument selected, not for our operation, but for the instrument selected, suddenly this becomes a worst case scenario. So evaluate the worst case scenarios and the impact it has on the Cems. And the installation requirements. How much space is required in the platform, right? I have also seen in few installations, the platform is just 1 meter wide, and we are going to install a probe which is 2 meter wide into the stack. Will we be able to safely maintain it? Or tomorrow if we want to remove and do it, will it be possible? So whatever we select, we have to be very clear and then see all those requirements, right? Whether it could be an in situ solution, which will something look like this, all the analyzers onto the stack itself, or it could be an extractive coming down and the system is in an enclosed area or a good area so that we are able to maintain it. So depending on our industry, our location, and how access we have, and what type of maintenance we are expecting, right? Please decide on this. And there is also possibility, this is one of the picture from Europe, where they have put a nice shade on the platform itself. The platform is so wide that the extractive analyzers, everything are kept on the platform. And they are fully covered with a shade. It looks like you are entering into an, okay, they don't have an AC out there, but then it looks totally conditioned. So I'm just showing you when it happens to an extractive hot wet systems, what all it comes. Why we want to look into that is you have a sampling filter unit, and then there are lines, sample lines, which will be slightly heated, right, to keep it above the dew point. And then it will come to an analyzer. It could be an IR, UV, whatever be the technology, what you would like to have. And then it might also measure oxygen, because that is one of the diluent correction we will have to do. So we will have to make sure that both pollutant as well as the diluent are measured at the same condition. It is not that we measure oxygen on wet basis and then we measure SO2 and other pollutants on a dry basis. Please consider that both are measured at the same conditions. Right? And then it comes to the dust measurement, calibration procedure, because most of the time we do a lot of investments on buying a nice dust monitor. I have seen that so many people invest so many things to buy a nice dust monitor, but then we always forget about that dust monitor cannot be calibrated with a cylinder. We'll have to do it only with a gravimetric method. So that means that also requires another insulation port, right? The gravimetric sampling port is here. So the access has to be clearly defined. Otherwise, it will be very difficult for us to keep a dust monitor calibrated. And that is one of the biggest topic, because there had been various experiences. One of the emission trading scheme, which is running in the state of Gujarat, they had a lot of experiences in getting a dust monitor calibrated. Right? So please consider these things before we select a technology, whether I want it on both the sides, whether I want it from one side installation so that the another side I can easily make. And calibration, I don't have to have different access points. There is no hindrance, right? So these topics, we should always do it. Right? This is one of the topic, I think, manual sampling, we will be covering it, how this is done, so we will get a better idea. But this is also an idea what we will have to keep before we specify anything as a technology or a model, everything that we want to be measured, right? And we know that for a gravimetric measurement, there are so many activities to be carried out, right? But then this topic of gravimetric sampling, this we will have to consider. We cannot have everything all together at the same place and then we expect that we will also do a gravimetric sampling. Okay, I buy 2-3 different analyzers. One extractive will be there, one part of in situ will be there, another dust monitor will be there, and we will be crowding. And then when it comes to calibration, we then say, let us complete the campaign faster. So that will not help us, right? So if we will have to go through all these steps, please consider this while you select, while you put your selection criteria. Right? So why this topic, this particular slide, is as you could see, if we don't specify whether it is a condensing or non-condensing, can we see the difference? Right? If it is condensing, then nothing is seen clearly. The dust monitors are generally optoelectric. Right? They are like cameras. They are seeing might be an absorption or they are seeing a scatter something, but they are like cameras. And if there is a condensation or a wet topic, then they will not be able to give you a clear picture. Right? Something like, looks like this, right? Scatter light, for example. It will not be able to. It might give a false reading. And we will not be able to calibrate it properly. And every time we do a performance audit, we will see that it is giving different data. First time installation is not the only topic here. It is about continuously giving you correct data. Right? So there could be like an extractive. So consider this. The whole system now it's changed. Earlier when we used to dust monitors, we know that it is 2 holes mounted, it's all good. But suddenly if your operating condition is different, now you are looking at a dust monitor which is of big in size and they have to be mounted near to it. So please consider all these things. There will be a huge difference for a small data which is missed. And then always comes the after-sale service, right? Typical services always we expect is supervision of installation and commissioning, data connectivity, which is already covered by Sudesh before, remote calibration function, preventive maintenance, on-call maintenance, and repairs, right? If something goes bad, anything can go bad, then how it will be repaired faster and where it will be repaired. And also there will be an annual subscription for data connectivity. This is the typical. But then there are certain things what we will also have to add will be selection and suitability of the Cems. We are talking about a lot of things on the Qual 1, right? US EPA and everything we write. But do we really follow it? And certificate is sufficient. We will submit it to Pollution Control Board and then say, yes, I have an instrument, this is a certificate. But if you really follow the Qual norms, then you will also have to make a compatibility study, whether that instrument is suitable for the particular application and particular mounting location. What will be the uncertainty at that mounting location? That also has to be done. Then we will be able to do this. And then installation validation, how to validate the installation. Today we are just calibrating, topic over, we give it to data, data starts moving, it is. But then the installation has to be validated. That is all, it's going to come. If not today, it is going to come. Because it is already there, part of EN 15267, or we talk it about US EPA anywhere norms, these are already part of it. So please consider this also as part of your procurement activities. And make sure that the vendor who can give you can support you in all these activities. So the summary topic is each step in the selection and specification is very important. We cannot skip any of it because already I skipped 5 steps. Because the original one was about a 10-step selection procedure, but then merged a few things and then skipped certain things, which is not relevant to our conditions. So already this has been condensed to 5-step selection, and we cannot skip further. And there is no one-size-fits-all solution. So there is nothing like, okay, one model, everything it fits for every application. There is nothing like that. And always choose a partner, don't choose vendors, right? So that's why I was also very skeptical when we say that tender specifications is trying to make everybody the same, but then you'll also have to see the capability and other things before you get into the procurement activities, right? And always assess the capability of them to do the topics. And please ever do not decide based on only the initial project cost. Include your quality of life, right? And already you are discussing about so many SMSs coming, and then you'll have to maintain, you'll have to call up, get your maintenance guy, talk with this, AMC, right? All those things. Please consider your quality of life also, right? Any questions?
Question?
First of all, thank you, sir, for taking us through all those details. My question is related to the alarming system. So, do we get options in alarming systems as well? Because, say, for example, the operator who is there, who is operating the stack or the boiler or whatsoever. So, I think he's the first person who should get the alarm if the emissions are getting higher. So, what are the options we have with respect to the alarming system?
Madam, we can have, first option is right from the instrument, since you are connecting it to your boiler operator control, right? That is your first level of alarm.
So it's like a hooter kind of thing?
It's up to you, madam, because if you are in a DCS room in a bigger boiler,
Yeah.
then you already have it coming up and separate screen for the environmental alarms. This is what we have seen in most of the installations. Or if it is a smaller boilers, then it could be connected to any one of your emergency alarms,
Okay.
right? So that you do it in the first step. The other step could be that there is already an SMS email notifications
But I
coming.
think that is always do not work, when,
No,
otherwise you have to put up
That
a,
is more of the exceedance, but you
Right.
can also have it before exceedance.
Yeah.
Let's say that when you cross 80%, right? Today when my geo data crosses 50%, I get a first alarm. You have already consumed 50%, right?
but
So
like
if you have a
in
normal
industries,
value,
farmers, we do not entertain more mobiles and all. So I think that is a second option.
Yeah.
So within the system, what options we have?
See, this can generate a digital output, right?
Okay.
And it is up to us to see what is the best one. It can create an digital RS485 or an Ethernet type of digital data, or it can just give a contact, right? We can utilize that contact to have a visual alarm or an audio alarm. That is
So
possible.
those logical we have. Also, one more question I have with respect to the MOC of your equipment, because this is a coastal side area where we see that the instrument or any metallic equipment, it gets rusted very soon. So do we have options with respect to MOCs as well?
There are various options available with MOCs, and then we can also have a lot of vendors. Everybody have their own way of handling it.
Okay.
Some people have an die-cast aluminum enclosures, somebody have an stainless steel enclosures, somebody have an epoxy coated enclosures. So there are various ways of handling this. And if you ask specifically that, okay, we are coastal, we have a corrosion issue,
Weather
then even
conditions.
the electronics can be, and tropicalized electronics we can get, so that the electronics, even though it is exposed, because sometimes people open and then they don't close it properly, then the electronics can get exposed. Then you can have a tropicalized coating for the electronics.
Thank you, sir.
Thank you, madam. Sir? Liabilities? Sir, can you?
So what are the general clauses on liabilities for the vendor or for the purchasers?
Liabilities on the statutory norms or on a contractual norms?
Contractual terms.
Contractual norms, it is between the vendor and the industry, right? Once you enter into a contract, you can put any of the liabilities.
No, what are the general clauses?
So general clauses, there is always a penalty, right?
Mm.
And that is a limited penalty you have. And there will not be anything unlimited.
Guarantees, warranties like that.
That will be there. You can get even 5 years warranty. You can get, people can give you 10 years warranty, right? Or you might get a whole system with 1 year warranty, but then that will keep working for 10 years. So that is where you will also have to decide that, sir, you buy a lot of things, right? Sometimes you get, somebody gives you, say, I give you a warranty of 10 years, but then after 15 days, you don't know where to go. But somebody says, I give you 1 year warranty, but then if something happens, I can go here. So that is where you will have to evaluate and access the vendor.
Good morning, sir.
Good morning, sir.
In the time of selection of instrument, some people came with RS485 communication. Some people came with 4 to 20 milliamps communication. In your point of view, which is the better? At the time of when I select the instrument, any instrument.
Since today most of the analyzers are digital, by that matter, their internal, they already have a digital signal processing, right?
Yes, sir.
They are not earlier type of one where millivolts are coming and then they are converted into 4 to 20. They are already digital signal processing. So I would only recommend that it has to be an RS485 or Ethernet, right? Any
Ethernet.
digital communication is good.
Okay,
so that you can also take it most places.
Yes, sir.
4 to 20 milliamps, even in the regulatory viewpoint, it is prone to tampering.
Yes.
But in a digital, this data is already stored. If you tamper also, it is known.
Okay, sir.
right? I'm audible, right? Yes, sir.
Sir, particle distribution is various in stack with respect to.
Okay, sorry. I couldn't get you, sorry.
Yes, yes. Particle sizes and distribution is very different in stack during the operation. The dust collector, how it can be reliable to detect the emission?
Right, sir. Generally, it so happens that if you don't change the fuel, if you are not changing the fuel, then more or less it is within certain standard limits. Let's say after an ESP, we can say it is about 5 micron. After back filter, we can say it is about 3 or 2 micron. This is the highest particle distribution. So your calibration of the dust monitor works good. But if you are planning to have various fuel, multi-fuel fired, then you might have to have different calibrations. And that is why this dust monitors has to be calibrated with your main fuels what you are going to fire.
But dust monitors are detecting only single pass or double pass only, but particles are distributing throughout the chimney. Some particles are escaping and some particles are detecting more values.
Sir, this is more about this technology. We might be discussed later, but for in general what we can say, most of these dust monitors, right, what you have as an certified dust monitors, they can handle this, right? Although they see a smaller volume, because we cannot have the whole plane of a stack and then we cannot measure. We cannot put 4 cameras into it and then we are able to see the whole stack and then do it. Yes. But whatever these dust monitors which are there, whether they are double pass, right, or they are a scatter light, backward, forward. So depending on your particular stack conditions and the type of fuel and the gas what you have, then the uncertainty can be fixed before you select it. So it is better that you give the situation, this is what the amount type of fuels we will be using, and this load conditions we will be varying, then you can select which will be the right instrument for you. Because some backward scatter light, you can increase the measuring volume so that you can reduce the uncertainty. And sometimes you might go for a forward scatter light where to have the very pinpoint and very less emissions, right? So, but that can be done when we discuss the product what you want to buy and your operation conditions both has to match. But yes, if you are going to use multiple fuels, then you might have to do different calibrations using different fuels and might use a different calibration curves. That is possible.
Right. Thank you, sir.
Thank you, sir.
Sir, in January, a circular came from CPC that in next 2 months or years, upcoming days, some software controlled interlocking facility will come. In that, that if our ESP or back filter is not working, then the software will have some multiple operational parameters and it will trip our conveyor belts or our operational process machinery, so that our industry operation will stop. So if...
Sir, I am still in the monitoring side. Please let me limit myself to monitoring.
My question is that with the current system, can we modify to that system, or there would be a separate commissioning for that thing?
Sir, today you are doing so many projects internally, right? It is like that it is a very small project for you, right? It is a very small project for you.
Yes.
It doesn't take a huge automation and you don't have to go to a big EPC to do such an activity.
Sir, for dust calibration, we are using gravimetric analysis.
Yes, sir.
For SOx, NOx, we are using calibration cylinder. In the stack flue gas flow also, we are installing the flow meter.
Right.
That is factory calibrated. Before installing, it is coming as factory calibrated.
Right.
Generally, for any flow transmitter, we do yearly calibration, like a DP transmitter with RFS plate or a Venturi. how to do the calibration for that? Inside calibration is not possible for that type of equipment in the chimney.
Understood. We cannot take the stack to somewhere and calibrate, or we cannot bring a prover to the stack to calibrate, right? So again, for the flow meters, depending on the technology of measurement, you have different verification processes. If you are having an ultrasonic principle of flow measurement, then speed of sound is used, because they measure only speed of sound. Ultrasound is sound. They measure speed of sound. So you already have a temperature, and the speed of sound is proportional to the temperature also. It varies with the temperature. So from the speed of sound, you can calculate, the instrument can calculate the temperature. So you can compare both. This is online, right? Without removing anything, you can do that. The other option is called a zero flow measurement, which you can do once in a year. Whoever be your manufacturer, supplier for an ultrasonic, they can come with a zero flow equipment where they can remove it from the stack, they will install it, and then they can do the zero flow. But zero flow, what they do is, they also calibrate the speed of sound. Because there is no flow, so that means, and the temperature is known, then this has to be the speed of sound. So once that is done, again you can put it there. You don't require a span point here, because this is only a time, transit time principle when it is an ultrasound. When it comes to any other type like DP and other thing, that means you might have to remove it, give it to any flow meter manufacturer or any other lab, then you can get it calibrated, or you can even do it in NPL. NPL also have a flow calibration. Or FCRI, you can take it anywhere and then you can get it calibrated with the element.
So the previous question that was asked by the gentleman, that there was a circular by CPCB that the equipment which you install in the stack will can trip off your process or operation. That was basically, that was sent to Pollution Control Board to think about it. And it was after NGT has pushed that why not we using that Cems monitor, you are non-complying for some time, they close it and you connect it directly to the operational control and you trip it off. This has huge implications, so there had been discussion behind it, so it is on hold. So there is nothing related to industry for this as so far. This is too complicated thing. I think we had enough questions. You still have time for during tea and all. If we try to match up with the timeline, will be very good. So we'll move ahead with this.
I have a question, sir. Thank you for a nice presentation. Actually, I want to ask a question. Here.
Okay.
Can you suggest whether we can put our CMS system on or off during the boiler startup, in oil firing especially?
Sir, I really didn't get it, sir. Can you please?
During the boiler startup, when we are putting in oil instead of coal, whether we should on or off the CMS system?
Sir, as I could see from what Sudesh was presenting more about it, you are not supposed to bypass the monitoring system, right? Only the system can be switched off, only your operations are off. You are not operating anything, then you might switch off the system to safeguard it and other thing. But if you are already in the startup or shutdown, there is always a provision to give a comment to the regulatory authority that this is only my startup. So don't expect that I will have the same emission, there will be a slightly higher emissions here. So you will have to put a comment that now after stoppage, we are starting.
Okay. Thank you.
You have your software, which is what do you call it, workflow in the corner. So you should run it. You should not close during batch process or startup or shutdown, but you should certainly mention that I'm going to, if it is planned, I'm going to shut down or I'm going to start up this time in the workflow. So it goes tagged with that time that this period of data is under shutdown or startup, so they will not consider it for average or comparison with the result.
So one more last question.
Yeah.
Just
Sir,
one thing.
Next during tea, please. We are already exceeding time.
Right, sir. Thank you.
Thank you very much, Professor Shankar.
And I will be available.
So we have not tea right now. You started late, so you have to wait. So we have one presentation on related on PM. We have our speaker, Steve Knopflet, He has almost 30, 40 years of experience from US, so he doesn't need much introduction. You will figure it out when he speaks and will tell you things. You will be free to ask questions, but just to match the time, I would have been very happy to take all your questions, but only thing is we started late waiting for you people only. So you have to suffer during tea. We will reduce the tea as well. So I invite him to continue, and after this we'll break for the tea.
Thank you, Sanjeev. I appreciate the introduction. While they are finding my presentation, I appreciate the opportunity to share my experience from the United States with you. You have an ambitious program ahead of you, and I am pleased to share as much as I can. This presentation is for you, so if you have any questions, please feel free to ask. And I understand that as an individual from the southern United States, that my dialect and my manner of speaking may be difficult for you to understand, and sometimes we use different words, even in the context of Cems. For example, correlation and calibration, obviously that's come up already. If you do not understand, feel free to ask. Feel free to ask here or later during the day. I am also doing this presentation rather as a switch hitter. Some of the slides that I will be sharing are Sanjeev's, so I appreciate his contribution to this presentation. Others are my own, if that presentation can be found. I will be sharing, excellent. I will be sharing some discussion regarding PM Cems, the different types of equipment that are available, as well as sharing the techniques that are used in the United States, as well as my interpretation of the Indian monitoring guidelines document, comparing the two, and making some recommendations that hopefully will allow you to have better success with your program. So what do you see in all of these pictures? Obviously, you're seeing particulate, or at least opacity by definition. And it illustrates that there is a potential to reduce emissions, and I would say as far as the emission standards that have been put in place by the government of India, controlling particulate emissions is perhaps the one that can have the greatest impact on overall health and quality of life, I would say, within this country. Now, these are very ambitious limits. Can they be met? And I have provided an example of a comparison of the U.S. standards with the Indian standards, using the thermal power plants as an example. And there you see that we report emissions in terms of pounds per million. You know, we kicked the British out before you guys did, but we're still using the imperial system. We're strange that way. But I have translated those to consistent limits. So for the units starting in 1971 through about 2005, that corresponded to about 100 milligrams per normal cubic meters. That's very consistent with the limit that has been put in place for units that were installed before 2003. Our MATS rule, mercury and air toxic standards, applied a 0.03 pound per million BTU limit, corresponds to roughly 30 micrograms per normal cubic meter. That is very consistent with the limit that's put in place for units here that were installed after 2016. Newer units in our country meet an even tighter limit in some cases, even down to 10 milligrams per normal cubic meter. That is much tougher to meet. That is also much tougher to measure. But it's an illustration that these limits can be met. However, it is more ambitious here in India given the coal characteristics. You have much more ash in the coal than we do in the United States. But regardless, in order to demonstrate compliance, in order to show progress, we need some sort of meaningful indicator to demonstrate that compliance. As far as PM monitoring is concerned, we've been trying to do that in some form or another since the beginning of the Industrial Revolution. And if you want to blame somebody or thank somebody, you can blame the French. A gentleman by the name of Ringelmann, he was a professor, he came up with a scheme to measure the degrees of blackness back in the 1800s, and he drew crosshatches on a piece of paper and would hold them arm's length or with a stick as the figure shows, and compared that to the blackness he would see in the smoke coming from a furnace in order at the time to deal with incomplete combustion and the soot that was all over Paris. Based on that, they could tune their furnaces and produce better combustion. Now, that was only for black smoke at the time, but it was applied directly to white smoke. You can blame California for that. They started that in the 1950s, and then readily applied by the US EPA and other countries as well. So if you wondered why you have a 20% opacity standard, it's simply because that's how Ringelmann decided to make his marks. If he made them differently, you might have a 15%. Now, this notion of opacity and monitoring opacity has been applied using a continuous opacity monitor, or as we sometimes abbreviate them, COMS, a continuous opacity monitoring system. And it is a way of measuring the visual effects, that opaqueness, using a light source and a detector. You can see a single pass monitor. Most modern comms are now dual pass, but the principle is the same. You have a light source, you have a detector. That light beam is crossing the stack and being attenuated to some degree by particulate in the stack. Now, with a double pass monitor, that's not going to be a completely linear relationship, so the monitor's got to take that into consideration. Also, there's usually an assumption that any dirt accumulation on the optics on one side that's measured is going to be the same on the other side, which might not always be true. But this attenuation is an absorption technique, and that is going to be following the Beers-Lambert law, which is illustrated there in the corner of the screen. Now I translate that right there to illustrate sort of a layman's description of what that means. And it really means that opacity is a function of path length, of concentration, and of particle size distribution, as Roland mentioned yesterday. Very importantly, of particle size distribution. And that can be affected by a number of things. Depending upon your source, what type of material that is being emitted. If we're talking about coal, it could be the type or blend of coal, the grind size, ESP or baghouse operation, electrostatic precipitator, ESP. Sorbent uses, if you're using dry sorbent injection for some type of acid gas control or carbon for mercury control, that will also be affecting it as well as other things. And fast forwarding a little bit, this is an issue not only with opacity, but also with any optical-based PM Cems. So moving on to PM Cems technology, different methodologies for trying to measure PM Cems. Opacity has been used for a long time as a surrogate, but opacity is just the attenuation of light. It's not really a pollutant, and it's not a direct measure of what we want to get at, which is reducing the mass emissions. So PM Cems is a way to better provide an indicator of those mass emissions. And there are several approaches that can be used. There are some non-optical approaches as well as optical methods. Now I will say you see asterisks on this slide, and that's a way for me to give you an early warning that those particular technologies are very limited in where they can be applied and their ability to measure PM mass for various reasons, and we'll discuss those. So non-optical methods include triboelectric, both DC as well as AC approaches, and beta attenuation. On the optical side, in theory at least, and in some applications, we could use opacity monitors and correlate them to PM mass emissions. We can use optical scintillation, or most often what's being used is light scattering. And that can either be an extractive approach, which we certainly need if it's a wet application, or an in situ approach. Now, as far as optical approaches are concerned, those are going to be based on absorption or scattering, which might show up as diffraction or reflection. Excuse me. Scintillation is an approach that is used in some situations, and I like to consider it as a twinkle, twinkle, little star methodology, if you're familiar with that English song. Twinkle, twinkle, little star, how I wonder what you are. Well, this is the same type of effect that you see when you see that twinkling star in the sky. You have scintillation of that light due to optical effects, in this case, the effects of the particulate passing through that light, and the detector will measure that. Now, this is an optical based approach, and in many ways very similar to opacity and its limitations. But it is an approach that is optical based and includes the entire path length. Other optical approaches, including PM Cems scatter, are really, when you consider them, a point measurement or a small area measurement rather than a measurement that includes the entire diameter of the stack. Many devices are based on forward or side scattering. These will provide better sensitivity, and I'll illustrate why that is in the next slide. They can be used both within the stack or as an extractive device. Another option is to use a backscatter monitor, and these devices can only be used in cases where we don't have water vapor. But they are a very useful approach because, as you can see in the top, I guess that would be your right-hand side, they do not come in contact with the stack gases at all. So they are very low maintenance devices. Now, just to give you a feel for what scattering is, I assume all of you have experienced scattering in real life, as illustrated by that picture in the left-hand corner of the screen. You go into a dark room, light is coming through a slit in the curtains, you can see that light beam. You're not actually seeing the beam, which is hitting the floor. What you are seeing is the scattering of the light by the dust in the air. And that's the same thing we're using to measure particulate in the stack. We can use an in situ device in the bottom left corner. That's an in situ device, forward scattering device, and you see that path link there at the end of the probe where the laser is coming from the base and being measured by the detector, which is at a 15-degree angle in this case, at the end of the probe. As I mentioned, the backscatter device, it will measure the backscatter, again, because that angle is decreasing as you go across the stack. It's really measuring just a small area as well, even though you may need a laser trap on the other side of the stack in order to keep that laser from bouncing back and messing up your measurement. Now, why in the last slide did I say that forward scattering is going to be more sensitive? It is because that figure there in the bottom right-hand corner, which shows the effects of scattering in different angles of incidence of that light to the particulate. And you can see that forward scattering gives a greater amount of light, if you will, that's being scattered in comparison to backscatter. Now, there's still plenty of backscatter that can be used by that type of measurement, but it's certainly going to be more sensitive if we're talking about forward scattering, and that's why many more providers use forward scattering for their measurement. Now, if we have a dry stack, the best way to handle an optical device is to do the measurement in situ, but if we have a wet stack where water vapor is being condensed, that's not an option for us because that water vapor shouldn't be treated as particulate, but it will scatter everything as illustrated by the last presenter. It's going to show up as particulate even though it shouldn't. So the way we get around that is we have an extracted device where we heat the sample gas, in this case using a thermocyclone, and then we use the exact same technique we would in the stack in this heated sample cell. So you see the exact probe I showed you in the last slide. We measure it, return the gas to the stack. We'll need an adductor. You see a blower unit there that's adducting the gas through this system, as well as a control unit. So a very useful approach for a wet stack. Now, an approach that is often used as an indicator for particulate in many industrial applications is triboelectric device. And this device here, I'm talking about a DC-based device, is going to measure the colliding particles exchanging their electrical charge with that measurement rod. Now, this has very limited applications because it is very velocity dependent. So if your velocity is changing, you're going to see that effect show up, and it will mask what's going on with your particulate. It can also be affected by water. It can also be affected if you are downstream of a ESP. So there are issues with using this device, but it's a good monitor of showing a bulk change. So it's often used as a leak detector for baghouse failures, but it's not necessarily a suitable device in many applications to correlate as a PM Cems. Another variant of the triboelectric principle uses AC instead of DC current, so we're not measuring the incident, but we're measuring the induction that's going on. This also is velocity dependent, but not as much. So it's a slightly better approach as far as potential PM Cems use, but I would again caution that this is is limited, and it's much better as a detector of baghouse failure than a mass indicator. Now, this next technology is the closest thing to a direct measurement that we'll be talking about. This is beta attenuation. Sorry, my graphic there covered up the name. It is not a continuous monitor, but it's close. So it's a semi-continuous batch process. The particles are being collected on filter paper. It's coming through the probe, being deposited on the filter paper that you see there in the rolls that are slowly moving across. In this case, this particular device has a single beta radiation source, and that beta radiation is going to be attenuated by the not only the filter itself, but any particulate that deposits on the filter. This radiation source, now the slide says it needs a high safety effort. Really, it needs a moderate safety effort. You may have essentially this detector in your house, at least if your smoke detectors are anything like the smoke detectors we use in the United States. They include a carbon-14 source. Same thing that's being used in this beta attenuation device. Carbon-14 radiation, beta radiation, is simply high-velocity electrons. We're not talking about gamma radiation or anything. We're talking about high-velocity electrons. Those electrons can be stopped by something as simple as my clothing, the layer of my skin. Now, we don't want to directly contact it with our skin, but if I'm wearing glasses, my eyes will be fine, or safety glasses, my eyes will be fine. Otherwise, protecting my eyes if I'm working closely with it is the only safety concern that I have. But because it is attenuated, readily by your clothing or something, you can see its potential for this application. Most of the radiation will be blocked by the filter tape itself, and then additional radiation will be blocked by the particulate that lands on the filter, and by that difference, measuring the tear before we sample and measuring the sample area after we sample, we can come up with an indicator of the mass. We measure the volume, we can get concentration. There are some consumables, obviously, with this approach. You've got to buy filter tape material. This is the table from the Indian Cems guidelines. It's a very useful reference, I believe. The one caution I would say is with respect to the minimum concentration values in some cases. Yes, you may have a detectable signal at that level, but trying to meaningfully measure a concentration down to 1 milligram per cubic meter is going to be very difficult to do because of the uncertainty of the reference method itself. I'm not sure if you have been introduced to Kermit the Frog in this culture. Certainly if you have not, you may want to Google him. You may have a new personal theme song. But during our conversation yesterday, and it came back up today, there was discussions of the difficulty of trying to calibrate or correlate a PM Cems. And Kermit the Frog, during an episode of the Muppets, if you haven't seen it, sang the song, "It Ain't Easy Being Green." And I think it's particularly true when you're especially dealing with a situation where you're trying to correlate a PM Cems. It's not an easy thing to do. And part of the reason is illustrated by this awful, ugly graph that I have right here. This is a graph that I put together, I think it was around 2015, of available PM Cems calibration or correlation data that I had from numerous utility sources. So these are all coal-fired power plants. Now, some of these coal-fired power plants have wet scrubbers, but as far as I know, all of these coal plants are pulverized coal facilities, so they have, some could argue, very consistent properties rather than, comparing cement plants or other facilities that might operate differently. Now, what you see in the blue lines, those are all correlations that were done for light scattering devices, and the red dashed lines are correlations that were done on beta attenuation monitors. Roughly 15% of the PM Cems that are installed in the United States are beta attenuation devices. Now, even with beta attenuation devices, where we would expect a more one-to-one correlation, the indication that they provide is not representative. But what it shows you is that it is extremely site-specific for a number of reasons, as we've discussed before. And I would say that PM Cems are different than all the other types of monitors we've been discussing this week. In the United States, we expect during the certification process, when we're doing a RADA for our Cems, SO2, NOx, CO2, what have you, to match the reference method right out of the gate. That is not the case for PM Cems. So instead of doing a RADA, we do a correlation, or what's called in your guidelines a calibration, in order to match the Cems to a reference method. And the problem is we're not directly measuring PM, even with a beta attenuation device. We have stratification issues potentially. Again, these are mostly just a single point or small area measurement. We have particle size issues. In some cases with beta attenuation, we have composition issues. What is it made of? What do the valence electrons look like? How likely it is to absorb those electrons? So the raw output may differ significantly from the reference method. So the correlations are going to be very site-specific. And it's really a lot to do with the fact that we don't have a dust-in-a-bottle calibration approach. Unlike our SO2 and NOx monitor, where we have reference gases, where we can match our output to those reference gases, we don't have a dust-in-a-bottle option here. And in some cases that's been attempted. The Electric Power Research Institute spent several years trying to perfect or evaluate a quantified aerosol generator, but we kept running into the same issue. Yes, we can generate PM, but can we match the particle size distribution that we have in the flue gas? So in order to get mass concentration in milligrams per cubic meter, we really need to calibrate each Cems using a gravimetric measurement approach. Now with the US standard, Performance Specification 11, we must attempt to vary our PM at least 3 different levels of PM concentration. So it's not unit load, but we're talking about PM load. That's the same type of approach that's being taken in the Indian guidelines. What happens if I can't? If I can't vary my concentration for a reason? Under both the US standard as well as the Indian guidelines, I've got to attempt, or the Indian guidelines say ideally. What if I can't? If I can't extend that data, then I'm going to be using potentially just a buckshot, a cluster of data at a single point, and then trying to draw my line through zero. And as this illustration shows, this is actual correlation data from a scrubbed unit in Ohio. If I simply had my baseline data, I'm going to come up with a very different correlation than I would if I actually was able to simulate control using detuning. And in this case, in order to get the 90% PM removal from a wet scrubber. So it's going to be very difficult, as this illustration points out, to do representative detuning on a baghouse or a scrubbed unit. And that may be particularly true here in India, where, as I've mentioned before, you have much higher ash coal than we do typically in the United States. Even in the United States, if I tell a plant manager that I want to detune my precipitator, again, I'm trying to representatively represent a failure that might actually occur. As Roland mentioned yesterday, it matters where the power is in an ESP, so we got to try to represent a representative failure. But if I tell the plant manager that I'm going to do this, he's going to look at me like I'm crazy. But it is the best way to get representative results, as we'll illustrate later. But the concern is you want to minimize that impact because you can upset the scrubber chemistry, particularly things like aluminum, the approach in the Indian guidelines. Let's talk about ash reinjection. Now, the guidelines don't specifically mention this, but like I said, it's specifically mentioned in the in the US EPA performance specification. And we have done it for sources in the United States. And this is an example. So this is Valley Units 1 and 2. They share a common stack. It's located right in downtown Milwaukee, Wisconsin. We have used this approach over several years. And one thing that's very peculiar about this source is that it was a consent decree source, which meant they got in trouble with the EPA and they agreed to put on Cems kind of as a research project. But they negotiated being able to use a opacity monitor instead of a standard PM Cems, if you will. So we were using ash reinjection at this site, and we did it over several years. A couple different companies, as you see, used their systems to reinject the ash. It was being injected prior to the ID fan, so in this case, we didn't assume any stratification because that ID fan would mix everything up. Pretty good spread there. But if you're looking at this graph, the first thing is that warning bells should be going off in your mind, because if you look at the curve, it's nowhere near linear. And it has a very steep slope. So that's the first level of concern. It was very unexpected as far as what we knew about similar sources that burn similar coal. So you see the ash reinjection correlation that we attained using ash reinjection there in the blue, and compared that to similar units where we did compliance assurance monitoring, a different rule, to develop a correlation using baghouse bypass and opacity. So you see significant differences in that correlation. And you see even a difference in that green line, which is much higher than the others. So why is that? I would argue that the problem with using ash reinjection with optical sites is that the ash will agglomerate. That is, it's not going to be the same as far as particle size distribution as you would with the native gas in the flue gas. Once you collect it, even though we're using the same ash that was collected in the baghouse and just reintroducing it, it clumps into large particulate, and it's hard to unbreak the egg, if you will. So we see large particulate that shows up as a lot of mass on the filter with our reference method, but large particulate provides very little scatter, so we see this huge curve that is not representative of what we would actually measure in a failure situation. The other thing that we can learn from this particular application is illustrated in this graph. And you may be tempted to use your opacity monitor, particularly if you have one already, as a PM Cems. But unless you're measuring PM concentration at a higher level, you will have trouble getting a repeatable value for compliance purposes using a COMS as a correlated PM Cems. So you can see the initial correlation there in the blue, as I showed you before. Under the regulations that are used in the US, you have to do a 3-level comparison with at least 12 runs every 3 years. So you see that. We did it first in 2006. We did our second one in 2008. We did our third one in 2011. And in order to pass, the RCA data needs to be within the red dashed lines, at least 75% of it, per the US rules. We aren't anywhere close to that. And what we're seeing is shifts in the drift of the opacity monitor, severely affecting the calculated PM or optical density from our opacity monitor. And that is to be expected. EPA in the US performance specification, PS1, even acknowledges that opacity is not a very good indicator at low levels. They say it's essentially a plus or minus 4% opacity measurement device unless you really go above and beyond. So we're seeing the effects of that. At very low levels, there's just simply too much drift. In the opacity monitor itself, it's not going to be a very good indicator if you correlate it for PM Cems. If you're measuring at higher levels, perhaps 100 milligrams per cubic meter, then you can get a reasonable correlation. There's still going to be noise in it, but it's a fair indicator. Below 50, you're going to see this effect. Don't do it, is my recommendation. So this is a comparison, again, my interpretation of the 2018 August Cems guidelines versus the approach that is used in the United States. In the United States, if you want to certify a PM Cems, there is Performance Specification 11. That's the initial correlation or any repeat correlation, and ongoing QA/QC that is defined in EPA Procedure 2. With respect to the Indian guidelines, you have an initial full calibration. Ideally, that is 3 runs at 3 different PM levels, so a total of 9 runs. You then use that to come up with either a linear or a second-order polynomial equation. And then monthly, you do replicate comparisons. And you would do a full 3x3 calibration if 2 of those consecutive monthly comparisons deviate by more than 10%. Excuse me, that should be more, not less than. A calibration dust factor adjustment, a recorrelation if you will, is only allowed if you do a full calibration, not a simple maybe 2 or 3 point test. You will repeat the full calibration after 12 months or after any major repair, quote, change of lamp, readjustment of alignment, change in solid fuel, or, quote, fuel quality. In comparison, The US procedures specify that you'll do an initial PS11 correlation using at least 15 runs at 3 p.m. Loads. Again, you have to at least attempt. Then you would do an annual RRA, relative response audit. That's a 3-run test at the at-found conditions. And a more rigorous test is done once every 3 years for sources under the MATS rule. And for that, you need at least 12 runs, and you need to attempt those 3 levels again. So similar to what you did during the PS11 correlation, but with 12 runs instead of 15. If you fail an RRA, you're forced to do a 12-run RCA. If you fail an RCA, then you are forced to recalibrate, usually based upon the RCA data that you've just collected. Now, there are also provisions if you operate above your correlation curve, you will need to do additional testing in order to extend that curve. You can, under the US scheme, recalibrate using a full PS11 test, really at any time, and in replacement of an RA or an RCA if you deem it. And it's going to be required if you have a PM Cems replacement, or you move it, or there's some sort of major change to your source. Now, under the EPA requirements, you're required to calibrate it daily. You're required to do a linearity every quarter. In comparison to the Indian guidelines, which I believe require you to do a calibration fortnightly, and require you to only do a linearity as part of this certification process itself. So the Indian guidelines will have you do a 9-point test. You will be comparing the raw output, in this illustration milliamps, although it could be any raw output, to the milligrams per cubic meter. And I believe it's consistent with the US guidelines, where you're correlating it in terms of how the measurement is actually made. So if it's made in situ, it's going to be the actual conditions within the stack. If it's an extracted device, it could be normal cubic meters. Then you are going to run your regression function, and you're going to implement that regression within your PM monitor, perhaps, or within your data acquisition or PLC. Again, under the Pollution Control Board requirements, you can only change that factor or correlation if you do a full-scale 3x3 calibration test. Now, some recommendations based on our experience when you're doing a correlation or a 3x3 calibration is you definitely want to get on-site analysis results. And the reason I say that is because if you don't get preliminary results from the stack testers when they're when they're on site, you're running blind. You don't know if it's going to pass. You don't know what the correlation looks like. You don't know if there's a problem. Now, these may not be final numbers. They may do additional drying and additional weights back at their lab, but you want to get at least preliminary weights to be able to assess, is this going to be a reasonable correlation, or do we need to do additional runs? I would suggest doing more runs than the minimum. Under the US scheme, there's an acknowledgement that sometimes you will have outliers from the gravimetric approach for whatever reason. It allows you to throw it up to 5, provided you use 15. Under the Indian guidelines, there are options for excluding data, but you have to justify the exclusions and describe the approach that you're taking. It could be a statistical approach or whatever. I would also suggest that testing at higher level PM will improve your correlation. Your correlation coefficient will be better. So you've got to spread out your points Otherwise, you're trying to draw a line again through buckshot or through cluster. Recommend that if you have a lower standard, and I would suggest that's probably going to be less than 50 milligrams per cubic meter, then you should probably consider running your samples at least an hour in order to get better accuracy. The rule allows 30 minutes. The guidelines, Indian guidelines allow 30 minutes, but you'll be better suited if you do longer runs. We've talked about scrubbers and baghouses posing challenges, but the best way to get representative results is by controlled detuning of your equipment. Now you want to seriously consider how you detune your equipment in order to represent an actual failure, because you want the correlation at different points along the curve to represent conditions that will actually exist when you have those high emissions. I would recommend for these correlation tests using EPA method 17 in situations where you have a dry stack. So EPA method 17 is the in situ filter, or if you have a wet stack using EPA method 5, or the European equivalent, which is ISO 9096. That method includes both the in situ and the out of stack filter. In dry stacks, you want to use that in situ filter because that minimizes the length of nozzle or other elements that are right before the filter, and so that minimizes the amount of rinse you have to use and the uncertainty that's associated with that in comparison to method 5 or that out-of-stack filter where you have to clean the entire probe length, rinsing it in order to capture all the particulate. So there's more uncertainty with that method. Speaking of that probe rinse, you definitely want to make sure that the probe, especially if you're using out-of-stack filter box, is clean before you start. You want to know, you don't know where that probe necessarily has been. It may be a terribly filthy stack where it's been before, or a very caustic material, a very oily material. You don't want it biasing your results. And the reason I am suggesting using the EPA methods or the ISO methods is because the Indian standard, as it exists right now, 1125.5, Part 3, lacks the details that would provide consistent results. So I would recommend revisions to that method in order to address things such as the analytical balance accuracy, the ambient effects, temperature, pressure, humidity that can affect your measurements, as well as probe rinses, things that we just talked about. And I would also suggest that accuracy can be achieved with fewer sampling points. That is illustrated in a few slides that I've provided in this tail end of this presentation that will be included with the materials that will be online, but we won't discuss those. Precision reference method testing is a must, particularly with lower standards, and you really need to have some prior planning or experience in order to do this. And finally, I recommend that India consider including incentives for reduced standard reference method testing for sources that use PM Cems and sources that can demonstrate better performance with their PM Cems. And with that, I will turn it back over to Sanjeev.
dust PM, Cems. Now we go into the gas Cems. What is the gas Cems? What is the important part of the gas Cems? What should we look after? That's switched on. But it doesn't switch. Yeah. Okay. Okay. So gases Cems means all the gas components, gas emissions, gases, pollutants, what are there, how do we measure them, how do we correctly design the system, what is it what we have to look after. Picture number one, where and what, you know that, I've shown that already yesterday. We're looking for this part, legislative monitoring, various gas components, various gas monitoring for a correlation like oxygen, humidity, flow, temperature, pressure, to correlate our data from the gas analyzers. What is it what we want to measure? Okay, total dust, opacity, heavy metals as part of the dust, if appropriate, inorganic compounds, CO, CO2, SO2, NOx, SOx, NOx, ammonia, HCl, HF, total mercury, organic compounds, total hydrocarbons, maybe individual hydrocarbons for some special applications, dioxins and furans, primarily out of waste incinerators, and then the reference values, oxygen, humidity, temperature, pressure, gas velocity or gas flow. Why should we measure at all? I mean, okay, Mr. Legislator asked us to do that, but why? Why should we follow him? Now, okay, we want to reduce the pollution. We want to reduce it. So we put in emission control. If we don't measure, we do not know how efficient our emission control works. So emission monitoring, Cems monitoring, tells us how efficient our control activities are. Otherwise, we don't know. Who doesn't measure doesn't know. Regulations, we had that already. We heard it multiple times. There are two different, slightly different approaches. Outside India, there is the Indian approach as well. I'm listing the external approaches. There's a US EPA approach in the US, 40 CFR 60, 40 CFR 70, ASTMs. No type approval for instruments. We heard that multiple times. Site approval, RATA tests, extensive site approvals after installation. Europe, there are ENs and country-specific regulations, like in Germany, TA Luft, BIMSCH stands for Bundesemissionsschutzgesetz, or Federal Air Quality Protective Regulation, and the individual regulations for the individual industries. At the moment we are, I think, at number 44 or 45, so it's a continuing process. Then the type approval of the instruments, only Qual 1 approved instruments, we heard that yesterday, only Qual 1 approved instruments can be used for legislative monitoring. And then there is the site installation test, the Qual 2. There are two blocks for gas monitoring. There is the process monitoring, and there is the emission monitoring, or Cems. Process monitoring is to optimize the process, control the process, save fuel, quality control of the product, safety of the equipment, safety of the whole process. Environmental monitoring, regulations, to fulfill the regulations, to protect the environment, to get a cleaner process, reducing of emissions, transparency of what I am emitting, I as an industry, avoid fines if I'm exceeding, and of course, maybe CO2 ETS or particulate ETS. Typically, it's a CO2 ETS. Return on investment here? Absolutely yes. If I control my process better, I get a return on investment. Here, if I'm smart, I can do it as well. As we heard yesterday from Kamertrasser, better monitoring means better control of the process, means a return on the investment. So yes, environmental monitoring, okay, if I avoid my fines, I might get, that's also a return on my investment. In general, environmental monitoring has lower return on investment than pure process monitoring. So what I always ask my customers and say, look, if you go for environmental monitoring, try to link your data, what you create, your measurements, what you do, with your process, and see how you can optimize your process by using these data. Gas analyzer systems. What the analyzer should be? They should be stable, they should be available, high availability, they should be accurate, repeatability, they should have correct detection limits, monitor what I need, what my emission sources is. There should be no interferences, so they should measure correctly. And of course, maintenance, I don't want to do any maintenance, so there should be no maintenance cost and no service cost. Be sure that's not true, and that's not possible. Everything needs maintenance, everything needs service, and that is very important. The overall system, Cems system, continuous emission monitoring system, should be simple to install, should have relatively low cost of installation, easy integration in my entire process, long lifetime, we talked about it yesterday, I would say 12 to 15 years is a good goal for a lifetime for a good maintained analyzer system, and of course the data should be available. There's something missing? What do you think? Is there something missing here? Unfortunately, exactly that one is missing. What is most times overlooked, and that's the sample handling system. Because up here is my sample probe, which in my stack, and I have to get that sample out of the stack down to my analyzer shelter in a correct way and with as least as possible interferences. So sample handling system is an essential key to the accuracy of a Cems, of a continuous emission monitoring system. Unfortunately, is very often overlooked. So what type of Cems technologies are? There are the in situ technologies, point monitoring or cross-stack monitoring. These technologies measure on wet basis. We had heard that term multiple times. Wet basis means including the humidity in the stack, which is a dilutant. Extractive basis, either the direct extractive hot or cold. Cold methods measure on dry basis. This measures also on wet basis. And then dilution extractive, again, in-stack dilution or out-of-stack dilution, both measuring on wet basis as well. So whenever I do wet basis measurement, because my reporting is based on dry basis, so I have to correct for the water content, meaning I have to measure the water, the humidity in the stack as well. Sample handling, sample conditioning, typical. Here is a sampling probe with a filter to keep the particulates out, because for my gas monitors, the particulates PM is not nice. I have a heated sample line. I have a sample gas cooler, sample gas pump, and the analyzer. And a possibility to introduce calibration gas. Two possibilities, either calibrate only the analyzer, or, as it is required in Europe and in the US, introduce the calibration gas at the sample probe so that the calibration gas flows through the entire way into the analyzer and the entire system is calibrated, or span checked, not calibrated. Calibration, as we heard that, is something different. So, for example, or this is a similar system here, introducing the calibration gas at the in front of the inlet filter on the sample probe, heated sample line. Europe requires a dual stage. European regulations require a dual stage sample gas cooler to take out the humidity, and with a sample gas pump in between the two stages. Reason is the sample gas pump produces slight pressure. That slight pressure might produce additional condensation, and that has to be taken out in the second sample gas or sample heat exchanger. I'm running a little bit faster so that I make up a little bit of time. So, sample handling system, material of construction, should not interfere with the sample gas components. So, for example, if I have use materials which interfere with my HCl or my HF, what I want to measure, or my mercury, what I want to measure, then I should look after that. So look after the materials used, the MOC of the sample handling system. Back purge, if there is higher dust content, back purge of the front end filter is a very good thing to do because it extends my manual maintenance periods. We heard it about representative point, sample point in the stack. It should be a representative sample. So minimum for India regulation says minimum 8 times internal diameter above the last change in flow or inlet into the stack. Minimum 2 times diameter below the outlet. Europe is 5 and 2. If that is not possible, there are stacks where it's not possible. 5 times or 8 times diameter after the last inlet is above the stack outlet, and 2 times inlet is way too close to the last inlet. Then in Europe, 2/3, 1/3 kind of rule is used. So take the length of the stack from the last inlet to the outlet at position 2/3 above the last inlet, or 1/3 below the outlet is then the position for putting the analyzers and the systems. Rule of thumb. But as we heard this morning already, then it is also required, much more required, to have measurements to find the representative point, so that I have laminar flow situation, as laminar as possible flow situation at the point of sampling. Inside my stack it's hot. I have high humidity. So that is why I need a sample gas cooler to take out the humidity before it goes to the analyzers. That means if I have at any point in the way a so-called cold spot, I might get undefined condensation at that point. That means losing of pollutants and creating very acidic, very corrosive liquid. So that any cold spot should absolutely be avoided. And unfortunately, I'm not showing you all these pictures, what I have taken from sampling systems where even on the picture you see the condensate dripping, and you hear it. Yes, sometimes heated sample lines are very long, have to be very long. Then the internal diameter of the sample line should be accordance to the length. The longer the sample line, the larger the internal diameter. Why? Because this tube creates a differential pressure. And if my differential pressure is too high, I'm not getting a sufficient sample flow through the tube. So if the tube is too small, then my differential pressure is too high. My sample gas pump might not even be strong enough to draw the sample. So always look on what is the differential pressure created, at what flow, at what temperature, and then decide on the size of the heated sample line of the sample tube. Look at that, or ask your vendor to look at that. Sometimes vendors don't think about everything. The condensate outlet, yes, that from the sample gas cooler is very acidic, very corrosive. So not just let it drip out, run outside, discharge it properly, because it's highly acidic, highly corrosive liquid. Technologies. So, in principle, we had that earlier, 3 different principal ways for a Cems. Direct in situ analyzers. A direct in situ analyzer sits in the stack, measures cross-stack or at a certain point or in a certain area, but it measures directly in the stack without any sample transport. So sample gas stays in the stack. Everybody thinks, wow, that's the best. I don't have to do it. But we'll come to advantages and disadvantages. It is good, but it's not always good. And it's available, dust opacity mostly is done in situ, oxygen and you see the components which are done in situ. Mercury as well, but be careful, this is only elemental mercury, what is measured in situ. You cannot measure total mercury in situ. Regulation asks for total mercury, not only for the elemental. But we come to mercury in the afternoon. Conventional extractive, that goes basically for all components, and is analyzer racks, analyzer shelters with multiple systems, individual analyzers, infrared, infrared, UV, or different technologies for extractive monitoring, dioxins and furans, even that there are a number of companies in the world, they offer dioxin and furan analyzers. They're all but one company, only samplers. It's one company who does a direct measurement in the low nanogram concentration range, what is required, but everything else are only samplers and have to be done then, have to go done then for laboratory analysis. The dilution-based means I take my raw sample gas, I dilute it with dry air, factor 10 to 1, 20 to 1, 50 to 1. This way I reduce my humidity, the percentage, the concentration of my water, so that my dew point is at, let's say, 2, 3, 4 degrees centigrade. But at the same time, and I don't get any condensation any longer, but at the same time, of course, I also dilute my pollutants. So typically, what I need is lower concentration analyzers, so analyzers for concentration levels which are lower than the standard emission monitors. As I said, infrared is a very nice way of monitoring because there are many components, pollutants which show bandwidth in the infrared, and similar is for UV. Other technologies, UV absorption as mentioned, chemiluminescence for NOx, FTIR as a multi-component analyzer, same as TDLS. Multi-component analyzer, that's the newest technology which is in the market available. FIDs, flame ionization detectors for hydrocarbons or non-methane hydrocarbons for air quality monitoring, or with combined with gas chromatography for individual components. UV photometry or cold vapor atomic absorption spectrometry for mercury with sample preparation for total mercury. We'll talk about that this afternoon. And then the well-known zircon dioxide probes for oxygen. Okay. Point monitoring in situ, pass system in situ, pass system in situ. The in situ Cems. What are the advantages? What are the disadvantages? Okay, said that already. No sample gas transport. Sample stays in the stack. We don't transport it to any analyzer shelter. So there is no interference with the sample gas, no washout in sample gas coolers. So no sample handling system required. So wonderful. Typically, there are multi-component analyzers, TDLS or DOAS, for example, used or UV based or infrared based. So it reduces the number of analyzers. It's built smaller. Yes, it's built up on the stack, but it's built smaller. So all looks nice and shiny. There might be some interferences. There might be unknown interferences between the pollutants in the bandwidth where I am monitoring. And it's difficult to calibrate them out. Don't forget, we're measuring on wet basis. On the analyzer, if I have one analyzer, multi-component, if one component fails, I'm losing all my data. Not only the SOX measurement, I lose everything. Path lengths in the cross-stack systems, path lengths is extremely important. Do I get enough sensitivity with my stack diameter equals my possible path lengths? So that is something what needs to be looked in. Then, as I already said, analyzer is up there. If I have to do maintenance, I climb the monkey ladder and I go up there to my platform. And if my instrument requires frequent maintenance, I'm frequently climbing up my monkey ladder. So people don't like that. So possibility that maintenance is not done as it is required. Because people just say, Bob, today it's stormy. I don't go up there. I'll do it tomorrow. And tomorrow I said, it was scheduled for yesterday, so today is too late, I don't go. And then, of course, some of the Cems instruments are installed in hazardous areas, explosive areas. Then in situ systems sometimes have a challenge because they might not be available for ATEX or IECX Zone 1 or Zone 2. But that is a minor issue. Extractive, we had that already. Sample probe, heated line, sample gas cooler, sample pump, maybe condensate detector, fine filter, sample gas inlet here or going up there, and the analyzers. In some cases, authorities agree to use one set of analyzers for multiple stacks, specifically if the concentrations are low or clearly always below the emission limits or very often below the emission limits, they might agree to that. That makes the whole system lower in investment cost if the authority agrees to it. Then you have multiple sample probes, multiple heated sample lines, a heated multiple sequencer, very important, a bypass pump. The bypass pump draws sample if, let's say, this sample line is connected to the analyzers. At the same time, this and this sample line is purged by the bypass pump so that fresh sample gas is available here at the switching point. And I change, and I already have now here fresh sample gas. That reduces my lag time between changing my samples. Again, if agreed from the authorities, or could also be done with a combined sample gas cooler and then a cold multi-point sequencer. As I said, this is another, again, the overview, sample probe, heated sample line, sample gas cooler, and the analyzers. So, conventional extractive. Relatively simple way of calibrating the entire Cems. Either I deliver the calibration or span gas up to the stack, to the sample probe, or directly to the analyzers, depending on the regulations. I have individual analyzers, so if my SOX analyzer breaks, my NOx analyzer still delivers data, and my CO monitor still delivers data. The analyzers are in the instrument shelter at the bottom of the stack, air-conditioned room. Easy for maintenance, so the only maintenance which has to be done is for the sample probe up on the stack. And measurement and calibration is on dry basis. So already what I have to report is what I'm getting. Yes, I need an AC shelter because most of the analyzers don't like high temperatures. Sample handling system, the maintenance is at the tapping point. Sample gas coolers, depending on how their design is, will wash out certain amounts of pollutants. SO2 is very water soluble, so it will be washed out. And the washout, the best sample gas coolers have a washout of approximately 7 to 8%. The worst on the market have a washout of approximately 15 to 20%. So that has to be taken in consideration. That is, by the way, one of the reasons why the Qual 1 certification, if I today develop the most brilliant SO2 analyzer and I take that and go to TÜV and I want Qual 1 certification, I only get it together with the entire sampling system. And then my analyzer or my analyzer system is Qual 1 certified using this type of sampling system. If I change it to a different manufacturer, certifications no longer applies. So this is a very important point that change came about 5-8 years ago in Europe, that it was realized the sample handling system has a significant influence into the quality of the analysis, and that is why it's included in the Qual 1 certification. Oops, that was the wrong button. Dilution, so either in-stack dilution or out-of-stack dilution. It's relatively simple to calibrate the entire Cems. I deliver calibration gas to the dilution system, to the front end inlet. It runs through the entire dilution and sample transport. I'm not washing out anything because heated sample lines, because after dilution up on the stack, they use individual analyzers. Okay, and the service and maintenance is in the instrument shelter. The AC shelter, same as with conventional extractive. The dilution unit, service maintenance is up on the tapping point. Typically, as I said, we reduce the concentration of the water, so we reduce the concentration of the components of the pollutants. So very often I have to use air quality monitors, which are more costly than standard stack monitors. Then pressure is very important. Most people forget that the dilution systems work with critical orifices, and the critical orifice is inlet pressure dependent in the dilution ratio, what it creates. So it's very important to measure the inlet pressure. to the dilution probe or dilution system. And last but not least, my measurement is on wet basis because I leave the water in. But when I introduce calibration gas, my calibration is on dry basis. So that has to be taken care of in the data acquisition system. That was it. I hope I made up some time. And thank you, and now open for questions.
Questions?
Sir, good afternoon, sir. Actually, for analyzing the Cems spectrophotometry, earlier it was said, now it is infrared FTIR. What is the difference between spectrophotometry and FTIR?
Spectrophotometry might work on different wavelengths. For example, if I use cold vapor atomic absorption spectrometry or spectrometry for total mercury, that works on 354 nanometers. So in the UV range, infrared works in the infrared range, as you have seen when we go. Oops, oh, it's gone. Presentation is gone. Oh, I don't know what. Oops. Oops. Yeah, when we go back here, oops, here, come on, no. Here, so you see here, 3,000 nanometers to 1,000 nanometers. So we're in the infrared range. That's the difference between infrared absorption and spectrometry.
And, was there the Cems analyzers attached with this both spectrophotometry and infrared?
They're both available as analyzers. Some manufacturers use UV, some use infrared, some use both in different types of analyzers, and both technologies are available for with Qual 1 certification. So it all depends on the exact, to decide. If you want to ask me which one should I use, then I will answer with a question. Tell me about your sample gas conditions, tell me about your process, tell me about what is your plant, and then we can look into what are the components you want to measure, what are the concentrations you need to measure, and then we can look into which is the most suitable technology. So it is always deciding on what is my right instrument, my right technology to be used is always a site-specific decision. It's not a generic decision.
Thank you.
Any question?
The question was, is there a difference between process gas monitoring and Cems gas monitoring? There might be a difference in terms of concentration. In the process, the concentrations might be higher. And there might be a difference in the components, of course, what are used, and in the sample gas condition. In process gas monitoring, very often I have conditions with higher temperatures or very high temperatures and maybe higher or very high pressures inside the process tube where the stack is plus minus on ambient pressure. Typically it's draft, slightly draft, otherwise it doesn't go out. That's the main difference. On technology, what is used depends on the components, depends on the situation of the sample gas.
Sir, when the instrument is getting the Qual 1 certification, does the certificate include the vendor name of the sampling system?
Yes, in the certification, when you go to the Qual 1 page, what I showed yesterday, it shows not on the first page of the certificate, but on the second or third page or fourth page, and they're all available in English language as well, even that it's TÜV in Germany. And all the certificates are available, and it shows what kind of sampling system is used for that certification. Yes. The manufacturer and the type.
No question? Good. We are making up to the time.
Thank you very much.
Thank you very much, Ron. Yeah, next you have again Sonwarden on Cems installation and setting. So this is the only session. So, Son, over to you.
Good afternoon, everyone. So I'm going to discuss the approach to installation and setup for the U.S. Cems systems. And we'll try to go through this relatively quickly. But if you have any questions, please let me know. So the U.S. EPA approaches to monitoring are all coal-fired boilers and integrated gas-fired combined cycle combustion turbines must use Cems to monitor gas concentrations and stack flow rates to determine SO2, NOx, and CO2 emissions and heat input. Gas and oil-fired boilers and turbines typically use Cems NOx diluent systems consisting of a NOx monitor and either CO2 or O2 to measure NOx gas emission rates in terms of pounds per million BTU or nanogram per joule. Gas and oil-fired boilers and combustion turbines typically use hourly data. NOx diluent systems together with heat input rates from Appendix D of Part 75 are used to determine NOx mass emission rates. Heat rates are based on fuel analysis and certified fuel flow meters. So in the case of a combustion turbine, you will have a certified flow meter that is monitoring the amount of flow of gas to the combustion turbine, and you can use that flow rate along with the heat input to derive mass emission rates. This is a very generic drawing of a setup for installation. And here you can see where we have an ultrasonic flow monitor represented there with the sample line and calibration gases. So the location for Cems monitoring. So the placement of the sample probe under 40 CFR Part 75 Appendix A, that will reference 40 CFR Part 60 Appendix B, where the performance specification PS2 resides. For gas monitors under PS2, you install the pollutant concentration monitor or monitoring system at a location where the pollutant concentration and emissions rate measurements are directly representative of the total emissions from the affected unit. You select a representative point or path for the monitor probes or probe as the gas will pass so it will pass a relative accuracy test. For point monitors, you locate the measurement point within one centroidal area of the stack or duct cross-section, or no less than 1 meter from the stack wall or duct wall. Another consideration under PS2 is it is suggested that the measurement location be at least 2 equivalent diameters downstream from the nearest control device. Now this is important. This is a nuance compared to method 1, which we would use to maybe locate the reference method sampling system, where you are ideally 8 and 2 diameters from the nearest disturbance. This is from the nearest control device, so it does not actually, or you can actually place it farther away from where the control device enters the gas stream or the exit of the control device. Anyway, it's a very interesting little nuance in the regulation because you are not necessarily held to the same standard. Let's see. Anyway, the nearest point of pollution generation and or other point at which a change in the pollution concentration or emissions rate may occur, and 2, at least 1/2 equivalent diameter upstream from the effluent exhaust or control device. Continuous opacity monitoring installations, you install the comms at a location where the opacity measurements are representative of the total emissions from the affected source. So that's 4 duct diameters downstream from any disturbance. I pointed out the difference earlier, but that's from any disturbance. So that would be any tapering of the ductwork, any flange or transition in the ductwork could be considered a disturbance. And you have 2 duct diameters upstream from any disturbance. Condensed H2O or water vapor is not present. So as mentioned previously in other presentations earlier, water condensation is a problem. So droplets will cause a false positive. Additionally, installed comms must be accessible for maintenance. That means you have to have the appropriate platform and access for people to maintain the system. This is an excerpt from EPA Method 1 for upstream and downstream distances. This calculation 1.1 is actually the calculation that you use to determine equivalent diameters for rectangular ducts. You can also see in this drawing here that it tells you the minimum number of diameters where you are placed and the number of traverse points that you would be required to do for a reference method. But the important thing here is you can see where we have the upstream and downstream distances and how they play into the sampling system. So monitoring range and spans. So you have the maximum potential concentration. So this applies to SO2, NOx, CO, and O2. So this can be determined either through equations using fuel analysis, Cems historical data if it's uncontrolled, and table values from varying regulations for NOx. The MPC is used to determine the span and range of a Cems gas analyzer, and when required is used as a worst case substitute for data values. Then you have the maximum expected concentration. This applies to units with add-on SO2 or NOx emissions controls, such as scrubbers or DNOx systems. It represents the maximum controlled value for NOx and SO2. The initial MEC determination is based on an expected average design removal efficiency. So whatever the design removal efficiency is of that control device for that pollutant, you can apply that to your maximum potential concentration and come up with a maximum expected concentration. Certified SEM data, that's a minimum of 720 hours or more downstream of the control device, may also be used to determine the maximum expected concentration, provided the unit and the controls are both operating normally. So you can use historical data, but you have to have the minimum of 720 hours, which is roughly 30 days. You have the MER, which is the maximum potential emissions rate. This is used for data substitution as required. It is also calculated using the NOx MPC and minimum CO2 or maximum O2 concentrations. You have the maximum potential velocity for your flow meters. This is used to calculate the maximum potential stack flow rate. Then we have the maximum potential stack flow rate, which is calculated using the MPV and the cross-sectional area of the stack. So the high span values are determined based on a multiplier of 1 to 1.25 of the maximum potential values. We have a dual span and range, where you would have a high and low range on some instruments, typically for SO2 and NOx. They are typically required for units with emission controls, and the low span value is usually derived from the maximum expected concentration. The full scale range must be equal to or greater than the span value. And range exceedances may require a readjustment of the analyzer if you did not actually calculate it out far enough. So if you spike over your intended range, you may have to make an adjustment if you find out that that's not a large enough window. So like before, I was talking briefly yesterday, I touched on initial certification. We're going to be kind of touching on that here. Part 75, Appendix A, includes procedures for conducting RADAs, linearity checks, 7-day calibration, error tests, and cycle times. 75.2 specifies the type of test required for initial certification and recertification purposes. These are two distinct events, and we have different drivers. Note, data acquisition and handling system verification requirements are part of the certification process and are also found in Section 75.2. Section 3 of Appendix A provides the performance specifications that must be met for each type of Cems certification and recertification test. So your facility, whoever is handling your permitting or your Cems monitoring, however that works for you guys, you have to submit an initial monitoring plan and notification of initial Cems certification at least 21 days prior to the starting of the certification testing under Part 75. You have to conduct all required testing for the Cems system or systems to be certified, to include the 7-day error test, linearity check, cycle time response, RADA, and bias test, which we talked about yesterday, and the data acquisition and handling system verification. The initial certification must be completed within 180 days after a new acid rain program unit commences commercial operation. For a newly affected acid rain program unit, the testing must be completed within 180 days after the date that the unit becomes affected. That's two different things. So if the unit was already existing and then becomes affected, then you have 180 days to test. For non-acid rain program units subject to Part 75, testing must be completed by the date specified in the applicable regulation, which can vary in the U.S. We have several regulations that layer on top of these, and so the primary regulation would dictate that time. That can also be modified by the state Department of Environmental Quality or Pollution Control Board here. That could come in and say, well, we want you to test it sooner than what's allowed. The federal regulations typically just establish a minimum requirement. The state can always make that more restrictive. Upon successful completion of all certification tests, the monitoring system is provisionally certified. A certification application must be submitted within 45 days after completing all the certification tests, and the administrator has 120 days after receipt of a complete certification application to review the application and approve or disapprove the certification. So just because you passed all the tests doesn't mean that they still have the right to disapprove your application if they don't like what they see. This is a typical Cems data flow. This kind of just shows where you're taking the measurements, in this case on a common stack, and you have a primary and redundant analyzer system, which is not unusual in the United States. That allows you to have a backup system if the primary system goes down, so you can have maximum data capture. So from the instrument, you can see we go through a data logger type system. In this case, we have 2 separate data loggers because we have a primary and a backup. Goes to the station computer, where calculations and the main database storage resides, and from there we generate reports out of those database stored files. So we have data processing and calculations. Units with SO2 Cems on a wet basis calculate SO2 mass emissions rates in terms of pounds per hour in the US as follows, and you use this particular equation. Nearly all units with NOx diluent Cems calculate NOx emissions rates in terms of pound per million BTU using either these 2 equations, which account for either O2 or CO2. In equations F5 and F6, we're allowed to use a diluent cap, which can be substituted for the measured diluent concentration. So for at certain points with boilers or when a unit comes online, you may not have the CO could be low, and that throws in a inaccuracy into your calculations, not necessarily representative. So the EPA has allowed for you to cap the minimum amount of diluent gas to allow you to calculate a reasonable representative number. The dry basis F factor, which is a factor that we use in calculating emissions, represents the ratio of the volume of dry flue gases generated to the calorific value of the fuel combusted. The carbon-based F factor also represents a ratio of volume of CO2 generated to the calorific value of the fuel combusted. And these are used depending on the type of system that you're using, whether you're using O2 as a diluent or CO2 as a diluent. These are published typically in EPA Method 19 is a good example of that. Equations F5 and F6 assume complete combustion in the absence of processed CO2. In view of this, the equations will not work for sources such as Portland cement kilns or for combustion sources if carbon capture and storage is implemented. Data capture and reporting of hourly averages. Hourly averages are computed using at least one data point, normally a 1-minute average, in each 15-minute quadrant of an hour in which fuel is combusted. If a unit operates in more than one 15-minute quadrant of an hour and some of the emissions data are unavailable as a result of, say, a QA/QC test, like a linearity, if you're doing a zero and a span for a calibration, or a calibration check, I should say, for an example, or you're just performing maintenance during that hour, you can still generate an hourly average if there are at least 2 valid data points separated by a minimum of 15 minutes. So you could start at the very top of the hour if you have 1 minute in that first 15-minute quadrant, and it takes you 45 minutes, 46 minutes to do the data or your maintenance activity. As long as you have 15 minutes that separate it, you can still have a valid hour, which is useful because that helps minimize the impact of maintenance activities on data capture. The owner or operator must use all valid data recorded during an hour to calculate the hourly average. All data points collected during an hour must, to the extent practicable, be evenly spaced over the hour. So for missing data, for any operating hours in which quality assured data are unavailable due to the maintenance, QA tests, or out of control periods, substitute data must be reported in accordance with Part 75. For Cems, substitute data values become more conservative, trending to increase reported emissions as the percent of monitored data availability decreases. So if you're being rewarded for having the maximum amount of data capture, but the more that declines, the calculated emissions become more punitive. The percent monitored data availability, percent monitored availability is the ratio of the number of quality assured hours to the number of operating hours over a specified period of time expressed as a percentage. When a unit has 8,760 hours or operating hours, then you start calculating your percent monitor availability based on the DAS on a rolling average for that 8760. Incidents that may result in missing data. You can have monitoring system malfunctions like a critical component failure, sample pump, monitoring system out of control due to a failed QA test, such as a daily calibration. You could have a failed linearity, or you could have a failed RADA, which means that 1 hour after you complete that, you are out of compliance. Required QA tests not performed by the deadline. So if you miss the deadline for that, you are out of control, so your data is no longer valid. If the monitoring system is offline for routine maintenance or required QA/QC activities, you still are expected to use data replacement for those time periods. Improper application of the Part 75 regulation or associated policy guidance. So if you do something that's not in line with Part 75, they can invalidate your data for that. In the United States, we do have a version of electronic reporting. It's through ECMPS, which is the Emissions Collection and Monitoring Plan System. This is an electronic data collection where we report our Cems data on a quarterly basis through the system. Affected sources are required to use ECMPS client tool to make 3 types of submissions. One is your monitoring plan, which you are required to develop prior to the implementation of your Cems. And that is also a living document like your QA/QC plan. Therefore, you can continuously update that, but that is a digital holding place for your monitoring plan. You have certification, recertification, and QA test results are also uploaded into ECMPS. And then you have quarterly emissions reports. So where we don't have a continuous feed going to the Pollution Control Board or the state or the EPA, we provide that on a quarterly basis, and those are submitted through this electronic reporting format. So monitoring plan data includes monitoring locations and relationships, unit information, maximum rated heat input, applicable programs, monitoring methods, fuel types, and emissions controls for that affected unit. Monitoring system makes, models, and serial numbers. So if you change a monitor out because it's time to replace it or you're upgrading it for whatever reason, you need to go back and revise your monitoring plan relatively quickly and make sure that it is kept current. You have Cems, MPC, MEC, MER, and MPF values that we discussed earlier. Spans and ranges are all contained in your monitoring plans. The formulas that you use to calculate your data, so for reporting in pounds an hour, pound per million BTU, if we're reporting concentration at 15% O2, for example, all of those formulas are provided in the monitoring plan. Then you have any qualification records, so if you have special definitions for your units, such as a peaking unit, or you're required to show or demonstrate the amount of hours of operation to qualify for that. So therefore, you would also include that in your monitoring plan. You have certification, recertification, and QA test data submitted separately, either prior to or concurrently with the relevant quarterly emissions report. The results of RADAs, linearity checks, flow monitor leak checks, flow to load ratio tests, 7-day calibration error tests and cycle time tests must also be reported. Fuel flow accuracy documentation needs to be included with that if you're using that to help calculate your mass emissions. Test extension and exemption records provided by the regulatory authority is also need to be included with that. Event records with conditional data validation claims and explanations for any out-of-control periods are also included in that. So emissions data, like I said, we do quarterly reporting typically. So you have daily calibration error tests and, if applicable, flow monitor interference checks. You have weekly tests, in this case for mercury only. You have hourly operating data, operating times, load bins, heat input rates. You have hourly records of CO2, NOx, and SO2 and mercury emissions. Fuel flow rates, stat gas flow rate, and as applicable to the monitoring methods used. All hourly records include monitoring component and/or system IDs. Hourly Cems records also include unadjusted and bias-adjusted emissions values. We talked about the bias adjustment factor yesterday. So we are presenting both sets of data so you can see for transparency purposes. The method of determination codes, so during a series of events, we flag these codes like a startup shutdown, or if you have a maintenance activity, that is mentioned in there as well. And then you have the percent of monitor availability calculations are also included. You have data quality assurance. So the ECMPS tool performs thousands of checks and recalculations of reported data to make sure that it's accurate. It will kick the data out and it will give you a message that says you're missing something if it notices something missing, whether that's real or not. The client tool will check the monitoring plan information, the QA and certification test results, and emissions data. The data must meet certain criteria before it will be accepted into the EPA database. Note, however, that the QA checks performed by ECMPS have their limitations. Just because we're putting it in there and they're calculating it doesn't necessarily mean it's being calculated correctly. Monitoring plan and QA data may be substituted at any time. Emissions data reports must be submitted within 30 days after the end of each quarter. All right, so that was kind of quick, but do you have any questions in regard to Cems placement, location of probes, data reporting?
Yeah, good afternoon. In an urea manufacturing plant, there is a big prill tower. Its diameter is 20 meters and the height of the prill tower is 100 meters. Do you? Urea. It is a fertilizer. Yeah, fertilizer plant. That's prill tower is there for manufacturing urea. The urea solution is pouring from 100 meters height. So they have a wet de-dusting system for controlling the emissions. High humidity conditions, the online analyzer is not working there. For particulate matter or an ammonia, these two parameters. Very big dia, 20 meters. Yeah. Yeah, de-dusting system. Okay. Thank you.
In your first slide, oil turbines, that is oil-fired turbines. Cems are attached to oil-fired turbines. Whether the clean fuel after clean fuel can get the for firing purpose. Is it Cems is required for that? Oil fire turbine. No, it is a clean fuel is there. Euro 4, Euro 3, Euro 6.
Not clean, still fossil fuel. So he's saying fossil fuel turbine, is there a requirement of Cems installation? Fossil fuel?
Yeah. I mean, you're going to be, it depends on the size of the unit and some other things that go into consideration, but yes, you would be required to probably put a
Is there any regulation in US for marine cargo movement ships?
So emission monitoring using Cems in cargo.
in
Sea.
in cargo?
Cems installation in ship.
Marine
in
cargo,
a ship?
vessels.
Yeah, I mean, there are some ships that you could use a SEM system on that.
Are there?
Yeah, my personal background doesn't have that.
Yeah, ships have, and that is required. It was originally required only for ships, for cruise ships entering U.S. American water areas. Now it's required for almost all ships to have PM monitoring, so opacity or dust monitoring, and in most cases also SO2 monitoring, and NOx monitoring starts coming up.
And what is the relation between maritime law and environmental law?
Yeah, the ships emit the pollutants.
Where? In ports or in
no,
sea?
everywhere,
High seas?
everywhere, on high seas as well as in ports. And in ports, there is a direct influence to the population living around the port. On the high sea, it's an influence to the water quality of the oceans. And if you take the total amount of ships what are cruising through the waters and emitting pollutants, it is a significant pollutant.
In India, there is a recent regulation for fossil fuels of below 1%, I think so, sulfur content.
In the heavy fuel oil, yes.
Yes.
Yes, correct. So that means automatically a certain concentration of SO2 in the emission of the ship. And if that exceeds, then there might be fines. I mean, there will be no fines in the ocean because there is nobody who is responsible. It doesn't belong to any country. But the moment you enter the waterways of a country, then these regulations apply. And as I mentioned earlier, Port of Hamburg in Germany, I mean, that is, everybody says Port of Hamburg, but it's 100 kilometers inland. There is 100 kilometers riverway to the port. And along this riverway, there are several monitoring stations for sulfur dioxide, focusing on the ships going on the Elbe River to the harbor or out of the harbor and measuring the SO2 concentration emitted, not directly emitted by the ship, but in the surrounding, and you see very clear correlation to the ships. And if that concentration exceeds a certain limit, then they're taking second action. Second action in that case means that a boat with a monitoring system follows the ship closely to monitor more accurately, ship dedicated, plus their police enters the ship, takes samples of the heavy fuel oil and analyzes it for the sulfur content.
Cems are working in that moment of also?
Yes, yes.
The same
yes.
Cems
Yes,
and
yes.
all these procedures?
Yes.
Thank you.
Add to this, thank you, Rohan. Sir, as you know that IMO is also has mandated a lot of limits other than every country to country. And any ship that sails, first thing they'll have to do is the fuel analysis. So if the sulfur content is less, then that fuel is approved and then they can move. If the sulfur content is high, because finally the ships are worried about money, right? They spend huge amount of fuel. So if there is more of sulfur, then all the engine suppliers, mostly the engine suppliers are like Wärtsilä, MAN and other thing, then they supply scrubbers to scrub the SO2. But whether the scrubber is continuously working or not, so now most of the ships in the international waters, they are all equipped with continuous emission monitoring system. So that data also has to be given to the authorities. Yes, we have this sulfur, higher sulfur fuel, but we have a scrubber and we are operating the scrubber and we are within the emission limits. So now most of the ships are having already an emission monitoring system.
Latest regulation. Okay, thank
Yes.
you.
Right. Thank you.
Thank you, sir. Thank you very much. Your 45 minutes lunch starts now. So come back early because one of the very important session you have right now for PM Cems.
Ah, yeah. So you all are being given some sheets which has some calculation written, and the presenter will also explain you all the aspect of it. Many of you might be aware of this, but it is better to know how they do it. So you are getting that calculation sheet. So if somebody is not there, please take for him as well. Otherwise, he will keep roaming and finding those seats again. And if everyone doesn't get it, please share with your colleague sitting beside you, because there's no scope of getting it copied right now. So we have plenty of seats available, so I hope it reaches to everyone. Yeah. So for the PM calibration, you have already heard, and by now, of course, I understand everybody knows that gravimetric sampling or monitoring, manual monitoring is the method for calibration. So it is very important and one of the most complicated, as some of our colleagues, some of participants here said this is most complicated thing. So yes, it is. That is why it has been part of this training. So we also need to understand the PM monitoring. That PM calibration, PM monitoring is the calibration method. So the speaker with us is Dr. Balbir Singh. He has 40 years of experience in environmental monitoring, also making these equipment. So this is the equipment that you see is the person who has also made this equipment. He has been into monitoring for all the 40 years, so he's the right person to tell you all the details. As I said, he's a president of Envirotech Equipment, and he has been kind enough to make this time with us here. And I don't think I need to share more words, just get directly to him. Balvirji, over to you.
Okay. Thank you, Sanjeev ji. So, as Sanjeev ji also told that stack emission monitoring is the most difficult. But I'm here to ease out it. My idea is that I will share my knowledge and we will discuss on various aspects of stack emission monitoring, which is a part of Cems calibration. So, obviously, as everyone knows why this monitoring is required, there are two aspects. One is the regulatory requirement or the compliance, and other one is the necessity for providing clean air to our citizens and to keep our manufacturing processes most efficient. So these two primary objectives are met with these objectives. What are the advantages with the Cems as well as with manual samplers? Cems, we all know, very quick results. Online results are already you get. And from the continuous results, you can compute the long-term averages, which is not possible with the manual samplers. Third one, of course, manual intervention is quite low. But in case of manual samplers, there are certain advantages. And the most important advantages is, this is the only method which is to be used for calibration of Cems. And in addition to that, there are some other advantages also. Capital cost is less. Maintenance is easy. Same instrument can be used at multiple places. You have not to install several samplers at several stacks or several places. Of course, calibration of Cems. And this acceptance trials, once you are installing the pollution control devices, at that time when you are installing the pollution control devices, Cems are usually not available. So the only way available with us is to monitor the stack emissions with the help of manual samplers. These are the two pictures. So what is the regulatory requirement? Though it is discussed several times, but as per CPCB guidelines, the requirement is that for calibration of Cems, one has to monitor, one has to take samples isokinetically at varied loads, at least at 3 loads, and that too thrice. And then he has to compute the results and compare with the results which are obtained during that period with the Cems. So this is the first requirement. You have to do the monitoring with manual sampler. Only then you can compare two results. And second requirement is the results has to be obtained fortnightly. It's not in 6 months or in a year. Every fortnight one has to measure the emissions, PM emissions, and compare it fortnightly. Third point is, if the two consecutive readings are varying, that is the difference in the results of manual sampler and that of, if the two readings of the Cems are varying by more than 10%, then again you have to calibrate it. And after calibration, you have to put a calibration factor, and that calibration factor is not to be changed without the permission of the state authorities or Central Pollution Board or pollution control committees. That is another regulatory requirement. You have to calibrate after any major repair, or you are changing the lamp. Any major repair is done, then you have to again calibrate your SEM with same procedure. Data capture rate of 85% is required. This is also specified in the guidelines. And who has to monitor? Only CPCB, SPCB recognized laboratories can do the sampling. This is also mentioned in the guidelines. So these are some basic requirements which are needed for monitoring, for sampling. The first foremost one is the site visit one has to perform, because many a times the proper porthole at the proper place is not available, and a team reaches there, and then they cannot do isokinetic sampling as required as per the guidelines or as per the IS. Let me brief here. There are the IS which mentions about this procedure is IS 11255, and this is also covered under US EPA standards. So US EPA standards covers two methods, US EPA method 5 and method 17. But in India, only method 17 we have adopted, because our stacks are not having any provision for installation of the stack samplers, which are designed as per US EPA method 5. And let me discuss here that what is difference between US EPA method 5 and 17. US EPA method 5, it elaborates about the monitoring where you are filtering the flue gas or stack gas outside the chimney in a heated chamber. And the probe pipe which is coming from the chimney to the filter, it is also heated. It is mandatory. So in US EPA method 5, it is more suitable for the stacks which are having more of moisture, humidity, moisture content is high or very high. Moisture content up to some level is almost present in all these stacks, but there are certain stacks, as somebody was talking about the prill tower of urea plant. In fact, urea plant prill tower, it is a solution where they are evaporating water. So it is having 40, 50, 60% of moisture content. So there US EPA method 17 at all doesn't work. But we do not have in India US EPA method 5 instrument designed for that. Why we are not having that I have already covered. Our stacks are not having provisions for installation of US EPA method 5 instruments. What is there in US EPA method 5 instruments? Probe pipe, pitot tube, thermocouple, all are clubbed together, all are placed all together, and then they are attached to a heated chamber outside the chimney, so it becomes a quite heavy system. It cannot be held by hand by any person. So there should be an arrangement on the stack where it can be bolted. So that arrangements are not available, and now also we are not keeping such provisions in our stacks. So we are continuing with the method 17 only. In method 17, the filtering system that is called thimble or filter, that is kept inside the chimney. So it is at the same temperature what is the chimney temperature. So there is no need of there is no provision of condensation. If it is condensed, then it is condensed after filtration. So there is a ease in the use of this method, and because as we know it's a very tedious task, so we have kept in mind that we should go with the US EPA method 17, which is easy to assemble, easy to handle, easy to do. There are so many points to be considered while visiting the location of monitoring site. It is always better if you are having the knowledge of the velocity profile, temperature, moisture in stack, because as I have told you, very high moisture, this method doesn't work. So you take it granted, the moisture is very high, this method is not applicable in good sense. Restrictions on using equipment and intrinsically safe area. There are several places in the plants like your refineries or petrochemical plants, you cannot carry the normal instruments. There is a requirement that instruments should be intrinsically safe. So this you must know prior to going to the site for monitoring. Appropriate measurement equipment like length of pitot tubes. You went there and the chimney diameter is 6 meters. Okay, very nice. So it will help me. So appropriate instrument means you should have the appropriate length of pitot tube, thermocouple, and probe pipe, depending upon the stack size of, diameter of the stack. And next point is competent manpower. This is the most important point. And how this competency is developed, there is no shortcut. The only way is do stack emission monitoring by your own hands. May I ask a question? How many of you have done stack emission monitoring? Please raise your hands. So it's very few people who have done stack emission monitoring. So in that case, I have to go very slow because you will not understand anything what I will be speaking here. There are several aspects. So I will leave general points. I will go to the method. How to do stack emission monitoring, what are the pinpointed points. I will discuss those points. Of course, a person who is having phobia with height, he should not climb to very high stacks. This I have felt once. When I went to a certain height, then I felt very disturbed, and then I was thinking how I will not go up, but how I will go back down to the ground. So this happens. So one should avoid if he is having height phobia. Personal protective devices are mandatory. One should have boots, safety belts, etc., with him. Gloves, chimney, because many times stacks have high temperature. And let me tell you, there are situations when stacks are having high CO levels, specifically in steel plants. And CO is very poisonous gas. So it is fatal for the human being. So in that case, one should have an idea that we are monitoring at a place where very hazardous gas is there. So the PPE or personal protective device should be available if there is any chance of leakage of CO, etc. Otherwise, there is there is no other solution except the person who is already on the stack and he is exposed to CO levels, he will die only. How to obtain the reliable and comparable results? One is we have to take the samples across the entire cross section of the stack. Are you able to understand what is entire cross section? Suppose the diameter is some 2 meter, 1 meter, 3 meter, 4 meter. Then inside the stack there is a plane. So from one end to the other end, that is called plane. So that, at that plane we have to take multiple samples. Monitoring objective is pre-planned. It is not like this that when we are going for emission monitoring for regulatory requirement of what is the PM level. It is not same as calibration of Cems. So your objective should be very defined. Sampling strategy will depend upon your plan, what is your objective. And of course, when you are reporting the results, the conditions which are prevailing over the stack or around the stack, you have to mention in the report. Like there is very high temperature to be mentioned, hazardous conditions to be mentioned, likewise. Yes. The recommended methods has to be adopted. This is one criteria. It is not that somebody has told that this is the way of doing stack emission monitoring. That will not work. Because there are several scientific considerations in the formulas, and then finally that impacts the results. The basic primary methods should be considered. Whenever you are doing some part with your some knowledge of computation and all that, but the primary objective, primary method should be in the center of the study or in the measurement. The most another very important aspect is to get the representative sample across the plane. Across the plane means inside the entire cross section of the stack, you have to have the isokinetic sampling. For that, a number of traverse points are to be selected as per the guidelines, CPCB guidelines, or as per the IS 11255. It is already mentioned there. In all other US EPA methods, same procedure is given there. The idea of selecting a number of traverse points is because when there is some process is joining the stack or chimney, then there is not uniform flow at the point of junction. it becomes uniform after certain height. So there is a 2D, 8D standard and selection of traverse points. Traverse points you have to select at the after considering 2D, 8D norm. I will explain in the next style what is 2D, 8D. So from the top, when there is a monitoring platform, there is 2 times of the diameter distance it should be there. And you see here at the bottom, there is an inclined portion and there is a straight portion. So this straight portion should be at least 8 times of the diameter where you should have a monitoring porthole or platform. There should be a porthole that is also a specific size. It is specified in CPCB regulations as well as in IS. It should be of 100 mm diameter. Why it is 100 mm diameter? Because your thimble holder or the filtering device which you have to insert inside the chimney, it requires that much size of the diameter of the porthole. Where it should be 5 feet below the porthole should be the platform, or one can say the porthole should be 5 feet above the platform. Power arrangement should be there at the platform. Most important, access should be easy. It should not be very difficult to access. This slide shows how to cover the complete section. So for this, you see here, there are 4 portholes, A1, A2, B1, B2. So there are 4 portholes at 90-degree angle at 4 different sides of the chimney. Why it is required? When the diameter increases from it is above than 1.5 meter, it becomes difficult to cover the entire stack cross section from one porthole. So at least 2 portholes are required, 2 at 90 degree. For stacks which are having diameter more than 3 meter, then 4 portholes are required. So this has to be considered before starting any monitoring and before planning the monitoring. What is the size, how many portholes are available, approaches available, and all that. The whole idea is that we have to cover the entire plane of the chimney or stack. So these dark dots are the traverse points. These traverse points we select. There is a table in my next slides I will show you. Idea is we are covering the entire cross section of the stack. Now as per the stack diameter, the number of traverse points are already specified. I remember many people do not follow this, that they simply assume that it's a small stack, a small diameter stack we took at one point or 2 points. That should not be done. Because the protocol, the procedure, the IS, every document, every SOP, they ask for this table. One has to refer this. So for, you see, for more than internal diameter, which is more than 5 meter, how many traverse points are there? 52. 52, not from one end. So this has to be covered from all 4 sides. These 52 points are to be covered that way. Up to the 1.2 meter, one can do from 2 portholes. Now point is when some stacks or some ducts are there, then there is no diameter, then how to get the equivalent dia? So there is a formula. The equivalent dia is 2 length into height divided by length plus height. So if there is a duct, or you can say length into width, so 2 length into width divided by length plus width will give the equivalent diameter. And then with that equivalent diameter, you will refer this table for calculating the number of traverse points. Now suppose you have your traverse points have come 12. How it will be located inside the duct? So this is the distribution inside the duct. You see here how you can cover these 12 points. You have to have 3 portholes and then 4 traverse points in the line of each porthole. That way you can cover the entire cross section of the duct. Suppose I have taken some 12 or 24 or 8 traverse points. Where these traverse points will be inside the chimney. So there is a table. You see at the first column, there is a traverse point number on a diameter. So this is 1, 2, 3, 4, likewise it goes up to 24 number of traverse points. So 24 is from one end. If you go for a very wide, very large diameter duct or chimney, maximum how many traverse points will be there? 24 into 4. So up to 24 the table is given. Take the example of traverse point, number of traverse point at diameter 1 and 2. Where these 2 points will be? In column 2, you see there are 14.6 and 18.4. What is this? This is the percent of diameter. So from one side, one surface of the stack, for example, take it from the porthole, where you have the porthole, the first traverse point will be 14.6% of diameter. If diameter is 1 meter, then the first traverse point will be at 14.6 centimeter, right? And where will be, only 2 traverse points are there. Where will be the second traverse point? 85.4% of diameter. So it will be at the other face of this stack. Likewise, for 2 traverse point, 4 traverse point, 8 traverse point, this is the table. One has to calculate the location, exact location of the traverse point. Now, what this diagram shows, suppose I do not have possibility of making a porthole at 2D, 8D, because stack height is not much, and I have to meet 2D and 8D standard. So that number of traverse point which was given in the previous table, that was for a stack which is meeting the 2D, 8D norm. But if it is not meeting 2D, 8D norm, the number of traverse points you have to increase. How much it will increase? This is the figure. You see here, from the right, there is a straight line, parallel line. Below is the 8. So it is meeting 8 times of diameter. And at the extreme top, you see 2D, 2 times of the diameter. So until and unless 8D and 2D is met, you see here traverse point multiples. And this traverse point multiple is 1. So when 2D, 8D standard norm is met, then you will follow that table. But 2D, 8D standard is not met. It is deviating from that. Then it is shown 1.5 times of diameter, 1 time of diameter. It is not meeting. It should be 2 from the top. It should be 8 from the bottom. Similarly, it is 5 times of diameter, 6 times, 7 times. Then this line is slanting line is giving more multiples. From 1 it is going to 1.5 to 2.5. So number of traverse points decided from the previous table will be multiplied by this factor, by this multiple. So this is also to be adopted while calculating the traverse points, and 2D 8D standard is not met. What is isokinetic sampling? Of course, the kinetic velocity of the flue gas or stack gas, whatever kinetic energy is there, at the same energy, kinetic energy, one has to take the sample. That is called isokinetic. And what is the factor for the kinetic energy? The velocity of the gas. So the velocity in the chimney or in the stack, whatever is the velocity, the same velocity we have to maintain in the nozzle from where we are extracting the sample. Our nozzle is the only portion of the equipment which is inside the stack. So we have to calculate a flow rate which gives the velocity inside the nozzle equal to velocity in the stack. That is called isokinetic sampling. So now I have done the site selection, isokinetic monitoring, sampling I have to do. Now I'm actually going to do the monitoring. When I'm going to sampling, the first point is I have to select a thimble. So I have the previous data or initial data available with me, what is the approximate temperature of the stack. Because I will carry the thimble which is suitable for that temperature. So this is the table showing the different types of thimbles. Thimble is the filtering media where you are filtering the dust when you are extracting a sample from the stack. So different types of thimbles are used for different temperatures of the stack. And how to condition the thimble before carrying to the field or site in the laboratory, you have to condition it, pre-weigh it. What is the criteria? That it has to be dried at 10 degree higher at the stack temperature. If stack temperature is less than 100 degree, if it is 40, 50, 60 degree, then at what temperature you have to dry the temperature in the laboratory? At 110 degree, even then 100. Because you can only eliminate the moisture after 100 only. So basic concept of stack emission monitoring, we are collecting a mass in the thimble, and then we are extracting sample at certain flow rate for certain time. If we multiply flow rate into time, we get the volume of the sample. So if we divide the mass by volume, we get the PM values. I have already discussed this. Why this is required, in fact? One is isokinetic sampling is to be done at this same velocity which is persisting in the stack. Why it is required? This clarifies this. Because there is a distribution of particles inside the stack, and that particles are of different sizes. There are some very fine particulates, others are some medium size, and some other particles are of coarser size. And they all have different momentum. When they are traveling in the stack, mass multiplied by velocity, they have a momentum. If you will not do the sampling at isokinetic conditions, what will happen? You see here, 50% isokinetic means I am extracting sample at half of the velocity, which is there inside the stack. What will happen? Because I am maintaining a low velocity, then heavier particles, they have high momentum. They will enter directly into the nozzle because of their momentum. But the finer particles, they will, because the velocity inside the nozzle is less than the velocity in the stack. So they will deviate from the nozzle. So finer particles will not enter into the nozzle, and more of heavier particles will enter into the nozzle. So what will be the net result? Net result will be your mass will be double the volume, because you are extracting at half of the velocity. So in the proportionate way, if you are not doing at the same velocity, your results will be affected. This is the second condition. Rather, this is the third condition when you are collecting at isokinetic flow rate. Both sizes of particles, larger and small, they flow at the same speed and they enter into the nozzle at the same speed. But in third case, when you are having the suction velocity higher than the stack velocity, what will happen? In that case, suction velocity is higher. In that case, finer particles will deviate towards the nozzle. So there will be a decrease in the results. Volume will be high, but amount of dust collected will be less compared to the isokinetic condition. So that's why one has to do isokinetic, 2 points. This is the basic design of our this stack sampler, which is shown here. What usually happens, one has to take the temperature of the stack gas. Then one has to take the differential pressure with the help of a S-type pitot tube. In Envirotech instrument case, there is a provision for simultaneous sampling of gases also. One can do only particulate also, or if one is interested to do the gaseous sampling simultaneously, then a portion of the gas, after filtering from the thimble, it is bifurcated, and then one can do the. This is set of impingers to be placed at the back side of the sampler. And the idea is the flow rate multiplied by the time gets the volume, or you can directly get the volume from the dry gas meter. In certain models, there is no dry gas meter, but there are some models where dry gas meter is also available. So what I was discussing, method 17, it's this. Thimble is inside the stack wall. Other things are same: pump, monitoring panel or stack sampler, impingers, and probe pipe and thimble holder, etc., etc. Method 5, you see, there is a filter holder outside. This is the difference in two. Now, when you are doing a stack emission monitoring, the first step is leak check. Assemble the entire train, switch on the pump, close the nozzle with the help of thumb. If float of the rotameter is the device which measures the flow rate. If float means there is a small pointer which is inside the rotameter. If it comes down to 0, means there is no leakage. So the first point is to make a leak check. If it doesn't come to 0, check for the leakages. Second is ambient temperature, measurement of ambient temperature. When you have assembled the entire train, thermocouple is already attached with the panel. There is a switch there. If you put the switch on the ambient position, it will give the ambient temperature. This is a little bit difficult. How to measure the molecular weight of the stack gas. So for measuring the molecular weight, you have to collect a sample from the stack. How you will collect? You have to collect a sample either in a toddler bag or in a glass bottle. And that glass bottle have a provision for trapping the sample so that it can be carried to laboratory. And in the laboratory, you will use the ORSAT apparatus. Then there is another IS available for operation handling of ORSAT apparatus. It is altogether a full exercise in itself, how to do ORSAT analysis. So one way is do the ORSAT analysis, and from that you get the concentration of CO2, CO2, O2, CO, and balance 100 minus sum of these three will give the nitrogen. So if once you get the composition of these four gases, then you can calculate the dry molecular weight. This is the formula. In the formula you see 0.44 is the molecular weight of the CO2. Molecular weight of CO2 divided by 100. Because you are taking the concentrations in percent. So likewise, you put this, you will get the MD, dry molecular weight. Right? Next step is determine the moisture content. Moisture content in this step. What is the procedure? You have to extract the sample, putting a thimble. That will be a dummy thimble because now, right now you are not doing PM sampling. You are doing a sampling for moisture. So you have to put a dummy thimble holder or filter. And then at certain flow rate, maybe any arbitrary flow rate, you draw a portion of the stack gas through a water bottle which is put in the chilled ice. Chilled water contained in the impinger, and that too is put in the ice. What will happen? Whatever moisture is there in the stack gas, when it will pass through the water, which is chilled water, which is again put in the ice box, the moisture will condense. And then you will measure the dry air will go to the panel, rotameter or DGM. You will get the volume from there. So one is the condenser for the moisture content, which is in large in quantity, but still some quantities escaped from the this bubbler. So what one has to do? A second impinger one has to put for the silica gel, which is in the second impinger you take some weight quantity of silica gel, and that silica gel is activated. Activated means it is in blue form. When it is in blue form means it will absorb the moisture. So whatever escaped moisture is there, it will be absorbed by the silica gel. So ultimately what will happen? The weight of the silica gel will increase by some quantity. So you will get some milliliters of water increased in the first impinger. There will be some increase in the weight of the silica gel. From these two, you will get the grams of water. Okay, you can get so much grams of water in so much of volume of gas. Right? Now this formula you see here. VV is the equivalent vapor. How you will calculate the equivalent vapor? The volume of condensate you have taken from the sum, which is the sum of the water in the first impinger and the difference in weight of silica gel of the second impinger. So if you combine these two, that will be the volume of condensate, because in case of water, the gram is equal to cc or ml. So it becomes the directly volume, either in, but you have to calculate it in the vapor phase, because in this stack it was in the vapor phase. So this is the formula which gives the volume of vapor, VV. Other things are 18 is the molecular weight of water, 1000 is to, because you have taken the sample in LPM, so you have multiplied by 1000 to get the results in meter cube. Tm is the temperature at the metering point, at the rotameter. So there is a provision in some of the samplers. It should be there that one can measure the temperature of the extracted gas before it enters the rotameter or DGM. So this Tm is that one. 273 is the normal temperature in Kelvin, and 760 standard pressure. P bar minus PM, this is P bar. You have to take the barometric pressure reading. Either you should have a barometer with you, or you Google it and you will get the barometric pressure at that place from the Google. You have to put that value minus PM. What is PM? PM is the value when you are extracting a sample, there is some pressure drop inside the sampling train. So that is the PM. From this dry molecular weight, you have to calculate the wet molecular weight, MS. This is the formula. BW0 we have already derived in the last formula. Simply put 1 minus BW0 plus 18 plus BW0, you will get the wet dry molecular weight, wet molecular weight. Next step is determination of stack pressure, absolute stack pressure. This is also required. Absolute stack pressure is derived from the static pressure. How one has to measure the static pressure? It's mentioned here. For this, disconnect positive end of the pitot tube. Their panel, there are two ports, positive and negative for the pitot. Disconnect the positive end from the panel. Usually when you are measuring the differential pressure, pitot is put like this. But in case of measurement of static pressure, you have to keep it like this. And you have disconnected the positive end. Whatever pressure comes, whether it's positive or negative, take it and then put in this formula, you will get the absolute pressure, PS. P bar is the atmospheric pressure. Delta P you have got after disconnecting the positive end. 13.6 is the, because the values which are coming on the panel are in the millimeter of water. But in this case, you need the values in millimeter of mercury. So we will divide that by 13.6. So after doing all this, then we can calculate the velocity. What is the velocity inside the stack? US is the velocity. This is the formula. Kp constant, formula constant. Cp is the pitot constant. It is supplied with the pitot. It is already engraved over the pitot. Delta P, you will be taking differential pressure at different traverse points. Pre-decided traverse points you will take. Delta P is, so root of this, divide by temperature of stack. You have measured temperature. PS, absolute pressure, we have already derived, and MS, wet molecular weight. MD, then MS. So now we can calculate the velocity of the flue gas or stack gas. Now comes the isokinetic flow rate. So at this velocity, we have to draw the sample through the nozzle. So if we multiply the area of the nozzle with the velocity, we will come to know the flow rate through the nozzle. And that will be the same flow rate which is existing inside the stack. So that's why it is called isokinetic flow rate. At this flow rate, we have to do the sampling. Usually 3 or 4 different nozzles are supplied with the stack sampler. Why these 3-4 nozzles are supplied? Because you will be getting velocities varying from minimum to maximum. Minimum means maybe 4 5 meter per second, or it may be 40 50 meters per second. If you will take that velocity, say for maximum velocity 40 meter per second, and you have chosen a nozzle, and any one nozzle, and if you will multiply the area of the nozzle with the velocity, the flow rate will come 400 liter per minute. You cannot set it inside the panel, because there is a limit of the rotameter inside the which is mounted with the panel. So to encounter this problem, in case of higher velocity, we will choose the lower diameter nozzle. In case of lower velocities, we will select the higher diameter nozzle. In case of moderate velocity, we will choose the middle size of nozzle. So this we have to apply to set the flow rate within the readable range of the measuring device, that is rotameter. Are you getting any what I am speaking? Okay. But the main thing is, until unless you will not do by your own hands, this entire exercise is really difficult. Now I have calculated the flow rate at the nozzle, but I am not measuring the flow rate at the nozzle tip. Where I am measuring at the rotameter. So there is some different temperature of the gas at the rotameter. The gas which is entering the nozzle, it reaches the rotameter at some different temperature. So its volume changes. So what I have to do? I have to convert it at the metering temperature. I will now consider the temperature of close to rotameter or dry gas meter, and then I will put in this formula. Nothing is there. The RS is the flow rate, which I have already calculated through the nozzle. Temperature at meter, temperature of stack, PS absolute, P bar minus PM0, this is P bar, we all know this is the barometric pressure at that place. PM0 is when you are drawing a sample, there is a suction drop and there is a vacuum gauge put inside the instrument. It is, you can read the difference in the pressure, and that pressure value is put at PM0, and 1 minus BW0 already we have discussed. So that way we will be able to set the isokinetic flow rate. That's all. Now we can do the sampling at this flow rate. For how much time? For how long? Selection of sampling duration. Usually 1 meter cube to 1.5 meter cube of sample, 1000 to 1500 liter of sample is adequate for any PM measurement. So if you are taking a 1000 liter sample, divide by the flow rate, you will get for how long you have to do the sampling. Maybe 30 minutes, maybe 1 hour, maybe 1.5 hour. This is calculating how you will calculate the volume which is discharged into the atmosphere. So this is velocity. This is the area of the nozzle into T, area through the, flow rate through the chimney into time, divide by 1000. So you will get the flow rate in meter cube, right? In case there is no rotameter, there is a dry gas meter, or simply you have to take the final reading of the dry gas meter minus initial reading of the dry gas meter multiplied by the calibration constant of the dry gas meter. Once you have done the sampling, you have taken the sampling for a specified duration, maybe 40 minutes, 1 hour, 1.2 hours. And you have collected some sample. From where you got the volume of the sample? Flow rate multiplied by the time. Now you have to normalize this volume because you are reporting results in milligram per normal meter cube. The volume which you flow rate you set was at the metering temperature. So you have to put again that volume in this Vg into this formula, then you will get the normalized flow rate. That means flow rate in normal meter cube. This is the last calculation. The weight from, of the dust, which will come from the final weight of the thimble after extraction of sample, doing sampling, minus initial weight of sample, divided by the volume of sample, normalized volume. This will give the results in milligram per normal meter cube. Right, sir? There is one more step. Once you get the results, you cannot report results as such. If you see these guidelines or IS, they ask that one has to report the results either at 12% CO2 concentration or at 11% O2 concentration. Where these two conditions are apply, for example, somebody is running a plant, some process, and pollution board people come to monitoring. They want to check a sample. If they do not run the process, they simply run the fan, what will happen? What will happen? Because process is a combustion process mostly. If it is not a dedusting process, normally the processes are combustion processes in some way or other. So in a combustion process, there is, when you are burning the fuel, there will be certain quantity of CO2. But if you are not running the plant at full load, because pollution board people have come to take the sample, they will down the process and they will be running with the fan. So what will happen? CO2 level will increase. CO2 level will decrease. And CO2 you have measured while you are taking the dry molecular weight. Now you have to convert this value after putting this in the formula 12 into 12% divided by observed CO2. So what will happen? If observed CO2 is 6, what will happen to the result? Result will become double of the what you have measured. So they will come to know, or they will multiply the result by 2 if you are not running the process. Similarly, when oxygen level should be, when you are burning the fuel, oxygen should be consumed. But if you are not burning the fuel, oxygen level will increase. There CO2 was decreasing in the previous case. Here oxygen level will decrease. So in this is the formula where 21 minus the standard oxygen. Standard is 11%. So 21 minus standard, if you have measured it, it has come 21 minus 5. What will happen? Denominator will increase. So again the result will be multiplied by some factor. So result will increase proportionately. So in all the results, one has to report the values of PM either at 12% CO2 or at 11% O2. O2 conversion is only applicable when O2 is less than 11. If O2 is more than 11, then it is not applicable. Some pictures of stack emission monitoring. The worst way of monitoring. One should never do this. So if we really want to improve the air quality, what we have to do? We have to control emissions. That's the overall summary. thank you for the patience hearing. I expect there must be several questions from your side. We have supplied one data sheet to all of you. Okay? So you see here some terminology, there is a difference in terminologies. In the first sheet, which is on the Envirotech Instrument Private Limited letterhead, but the formula which I have discussed, US equal to KP CP root delta P by TS into PS by TSMS. The result, that formula and the formula here, the difference is here. Here we have assumed that instead of taking the flue gas after doing the proper Orsat analysis, or this flue gas analysis one can do with the flue gas analyzer also. That I have not discussed. If you have a flue gas analyzer, you can do with that also. So, but with both the formulas, results will be same. Why we have put like this? This is a simplified term of the same formula. If you will do, you will come to know, because as annexure where moisture calculation sheet and stepwise we have shown you, step 2 calculation of dry weight, then other things. So tomorrow I will be there, my team will be there, we will be doing the field exercise somewhere in the industry. We will be demonstrating how to use this instrument. Whatever I have spoken to you, how to take temperature, how to take velocity, how to do the, how to take a sample for flue gas analysis. Though we will not be doing any analysis, but we will show you practically how it is done. And because I say the participants number is very high, maybe all of you may not be able to see everything, but you can go through these data sheets, and then you have any specific questions, whatever comes to your mind, you can discuss with me. We will deliberate on those things, and we will correlate with the field exercise. So try to understand these data sheets and come with certain questions tomorrow, right? Okay, thank you so much. Okay. So when stack emission monitoring, I am using this term, but this in all references is for the PM-SAM calibrations, stack emission monitoring. Whenever you are doing any monitoring, you have to first write the date of sampling, time of sampling, name of a stack. Name of a stack means to which process it is attached. Is it a boiler stack? Is it a dedusting stack? Well, it matters. Boiler stack will have different types of gases inside the stack gas. But dedusting gas will be having only air and particulates. So name of the stack, operating load, whether plant was running at full load or partial load, you have to indicate. It helps in interpretation of the data. When you come with the results, all these information one has to collect and note down. Pitot serial number. Pitot serial number is given over the pitot. It is there. And by the side of that, there is a pitot constant also mentioned. It is engraved at the pitot. So 0.6 is pitot constant. manometer fluid. Why we have taken this manometer fluid? The earlier samplers, whether indigenous samplers or imported samplers, whatever it was, these all samplers were having a manometer for differential pressure, delta P, which in the formula I was discussing. So, still these samplers are in the market with the industry, with the users. But now the samplers which are presently we are producing and supplying, these are coming with the digital differential pressure. It is directly digitally indicating the delta P. There is no need of taking any fluid and density. So this part is eliminated in that case. So it depends upon the which type of stack sampler you are having. This I have discussed. Density of manometer fluid is required if it is a glass type manometer tube. Molecular weight of stack gas, we have directly written here. I have, there is a sheet with this as an annexure, and I have also discussed what is the molecular weight. So here this molecular weight, units are different only. That was in kg mole, this is in kg cubic meter. So only there is a difference of units. So whatever unit you take in all cases same similar unit, either a metric unit or other unit. Then moisture content in stack gas. Moisture content, how to measure the moisture, I have told. Do that way. Note down here moisture content. Initially you have to collect the sample from the field, take it to the laboratory, and then you will get the results. Calculated density of stack gas. It is same molecular weight of the gas. Now it is at normal temperature. Calculate the density of stack gas air at 25 degrees centigrade. The formula is simple here because here we have not considered the stack gas. We have considered there is air inside the stack. So I have also derived some of the results. I have computed. If for normal stacks, dedusting stack and some combustion stacks, like your cement plant kiln, power plant, in such cases, whatever CO2, O2 and CO content variation is there, but the variation in the results, it comes less than 5%. But I'm not saying that you should not follow. Protocol says you have to consider. This is a simplified that I have considered the density of air, not the gas in this stack. Of course, stack temperature you have to note down with the manometer. Thimble selection you have to decide depending upon the temperature of the stack. Stack diameter you have to note down. Only then you will be able to decide the number of traverse points. Number of traverse points you have to note down then from the diameter, and then distance of each traverse point. For this you may have to use a separate sheet if the diameter of a stack is very high. If diameter of a stack is 0.5 meter or 1 meter, you can put in this row only. Otherwise, diameter, if it is 3, 4, 5 meters, then you have to take a separate sheet for that. Stack diameter, this distance of each traverse point is over. Differential pressure at each traverse point. This is delta P. Delta P I have discussed already. And then velocity calculation. The formula, only terminologies are different. Basic principle is same, only units are different. what you can do, those who are familiar with the stack emission monitoring, the IS or CPCB guidelines says to do calculations or monitoring the way which I have presented. This is the way which Envirotech gives the method of monitoring in our manual. So this is prepared keeping in mind that stack emission monitoring should be done in a simpler way as far as it is possible. Otherwise, it is very difficult. Really calculating so many traverse points and then it's really difficult. So you have to, with your experience, you have to escape some of the steps. But it you will come to know with your experience only that what are the steps which are not very much important, we can escape, or we can take some certain value against that with the experience. We are repeatedly monitoring any stack, and we know that what is the composition of a stack gas. If it is running at the same load, it will remain the same. So every time you have not to take the readings. You can take that value which you have previously measured. Finally, isokinetic flow rate, you have to calculate velocity multiplied by the area of nozzle and then converting it with the temperature at the metering point. So for different nozzles, this flow rate is mentioned already here. Nozzle, which nozzle you have taken, you simply mention here. Sampling time, now you know that I have to collect about 1 meter cube to 1.5 meter cube of stack gas. How much will be the time? So you decide your time depending upon the velocity or flow rate, velocity multiplied by the area of nozzle. Sampling time, flow to be set on PM rotameter. This is after conversion of the temperature at meter, right? Flow to be set on gas rotameter. If you are doing simultaneous sampling of PM as well as SO2 and NOx. NOx, of course, there is a altogether different method that cannot be done with SO2. For NOx, you have to do a separate set of sampling. You have to use this sampler only for evacuating the NOx flask. Because in NOx sampling, a sample is collected in a evacuated round bottom flask. If you will go with the IS which I have mentioned, 11255 or respective US EPA standards. So that is the method for NOx. But SO2 you can do here, and some other gas if you want to do, SO2, ammonia, simultaneously with PM you can do. Initial suction pressure at metering point. So initial and final, when you are starting the sampling, there will be some pressure drop at the pressure gauge. And when you will complete the sampling, the pressure drop will increase. Why? Because there is some dust collection in the thimble. So there is more resistance through the thimble. So there will be more drop in the pressure. So you have to note down both initial at the start, at the completion of the sampling, the pressure or the suction pressure, which is given by the pressure gauge mounted over the stack sampler, right? Suction pressure at rotameter inlet, it usually is not more, because in, okay, yes. The rotameter inlet, that is connected with the pressure gauge. So this you will get from P1 plus P2 divided by 2, you will get the average. Okay. Barometric pressure, you have to either measure with a barometer or you Google it, you will get the barometric pressure at that place. temperature of flue gas at metering point we have discussed, temperature of flue gas at, okay, corrected flow rate, normalized flow rate I have told you, so that is there. Now finally, you have initially noted down the initial weight of thimble, and then after conditioning the thimble, after sampling, under same conditions, you get the final flow rate. So final weight minus initial weight divided by the volume, this gives the dust concentration. I think that's all in this. And this sheet already, line by line, I have covered in my presentation. And rest of the things we will discuss tomorrow. We will share our knowledge. We will discuss with you, whoever is available for tomorrow's demonstration. So once again, thank you very much to all of you. Any question is still remaining?
Any questions?
Sir, if we have a rectangular horizontal ducts, several rectangular horizontal ducts which are going joining to a circular vertical stack. So can we put our analyzers on these rectangular horizontal ducts instead of circular vertical stack?
If it is a horizontal or inclined duct, the criteria is the disturbance point is from where it was starting, and the other disturbance point is where it is joining the circular stack. So it should be, your porthole or platform should be 2 times of the diameter downstream, and at the back it should be 8 times of the diameter, irrespective of its inclined or horizontal.
Okay.
It may not be vertical.
Okay. Sir, what duct cast? Horizontal duct. Like a horizontal rectangle duct is going and it is joining to a vertical circular stack. So we suppose we are not we have not decided to put an analyzer on stack. We are deciding to put analyzer on horizontal duct. So what would be the spacing before and after of the duct?
His answer is correct, but rather the question should be, when you do the diameter, internal diameter, you know 8D, 2D, right? That is applicable for the stack, that is applicable for the duct as well. But when it is a rectangular duct, what is D? No, what? Yeah. Yes. So that is the question. It is not a problem of distance, problem of you get the right diameter to have. So if it is not 8D, 2D possible, normally it is 8D, 2D is not possible in the duct because it is normally a smaller distance. So that is where you also can find out in between maybe 4D, 4D or 2D. But in that case, you have to also do the stratification to find if that spot is correct or not.
What Sanjeev ji is telling, in fact, stack emission monitoring, first you have to consider the stack. If stack, for example, stack is not there at all, only small portion is there. If some condition is there, only then you can do at other place. Otherwise, stack, you have to, if you can get the 2D, 8D criteria fulfilled there, you have to put a Cems or a manual sampling port in the stack. Because stack emission monitoring means stack. But in very few cases, in certain limitations, when there are some limitations.
And the diameter you can calculate, length into width divided by 2 into length plus width. That's the diameter for rectangular. So any more question? How many of you have seen all the equipments required in PM monitor? So all remaining hands don't need know? Or how many yet doesn't know all the equipments of PM monitor? Sir, can you explain one by one? Can you showcase, show the equipment and tell them what is that? I mean, people should at least know these are the equipment, this is what it is called.
You can go on the, yeah. Yeah, yeah.
So in my presentation, I covered to take, first point was to take the stack temperature. I'm leaving the criteria, 2D, 8D, traverse point, this, that, I'm leaving that. How to use the stack sampler, what is a stack sampler? This is the temperature indicator. What is temperature indicator? This is a K-type thermocouple and a K-type pyrometer. It should, I have seen people, they are having a K-type thermocouple and J-type pyrometer. That doesn't match. That doesn't give correct reading. So there should be a thermocouple pyrometer. It is this one. There is a read button here. There are two terminals here. And over here it is written T and C. T/C. So thermocouple you have to connect. There are two terminals of the thermocouple. Thermocouple is this one. This is the thermocouple. This part goes inside the stack. Its length varies. This is 1 meter. It is available in 2 meter, 3 meter sizes. Not more than that. And Mr. Pradeep he has connected it. And right now, if we will switch on it and we will press this button, this will give the ambient temperature. What is the ambient temperature? And if you will insert this inside the stack and you will press this button, this will give the stack temperature. And you have to change the position. This is ambient temperature, 26. This is not as good as thermometer. It's approximate plus minus 1 or 2 degree. Yeah. So this is the temperature. Then I discussed about the differential pressure, delta P, and static pressure. So for that you have to use a pitot tube. Pradeep. So let me. So this is 0.5 meter length of the pitot. This is called S-type pitot. Why it is S? You see, this tip of this is like S. So these two terminals, at one terminal there is a positive mark, at other terminal there is a negative mark. So positive of this pitot, positive and negative of the pitot need to be connected to the, thoda upar karo, positive and negative of the panel. And there is a manometer here, this one, direct indicating type manometer. This manometer is giving values in delta P in millimeter of water. In earlier, the old systems, in place of this, there was a inclined manometer, glass tube manometer, and then one has to put a liquid. Usually red oil was filled. Red oil is lighter than water. Its specific gravity around 0.8. So you have to multiply the height which is achieved by the delta P, by the pressure or differential pressure, by the specific gravity of the red oil. But now in this case, because that inclined manometer is eliminated, so you will get the direct reading from here. You have to press this button, that's all. You have to insert this pitot, and you should keep it like this. Say this is the flow, so positive end of the pitot should face the flow, and negative end should be open to atmosphere. Inside the chimney, it is open to atmosphere. So it is giving a differential pressure, positive and negative. What he has done, he has connected the extension. So you will get this and multiple extensions. Depending upon the diameter of a stack, you can ask for the extensions. Otherwise, pitot tube is available in 1 meter whole length, 2 meter whole length also. But above that, there are extensions available. So you will get delta P here. You will having this position, you got delta P. Now I have to do the static pressure for computing the absolute stack pressure. What I will do? I will remove the positive from here. And this was the position for delta P for the velocity in the chimney. Now I am taking the static pressure. I will put it like this, horizontal. In this position, its two terminals are facing two walls of the stack. This will give static pressure. Values may be positive or negative in this case. If stack is having a positive pressure, value will come in positive, otherwise it will be negative. Then you have to put the positive or whatever negative in the formula as such. Static pressure value, and then you will calculate the absolute stack gas pressure. Right, sir? So now with this, I got all the parameters as per the formula. Velocity equal to KPCP root delta P TS by PSMS. This was the formula which I have presented to you. So Ks is the formula constant. CP is pitot constant. It is this is positive. Just a minute. No. 0.81. So its pitot constant is, it's 0.991. It's not 0.81. This engraving is a little bit hazy. So you will get pitot constant from here, formula constant. Delta P, I have already told you. Then TS, stack temperature we have taken. PS, absolute stack gas pressure after taking static pressure, converting it to absolute pressure. TS by PSMS. PS and MS is the molecular weight of stack gas in wet condition. So dry condition I have calculated MD, and then MS I have calculated after considering 1 minus BW0 in the formula. Until unless you will do with yourself, it is little bit difficult. I also feel so. So now you have calculated the velocity. Now you have to decide the isokinetic flow rate. So velocity is with me. I have to multiply with the area of the nozzle. Isko rakh dijiye. Take this. So normally with this sampler we are supplying these 3 nozzles. ऐसे दिखा दो. So these 3 nozzles have 3 different diameters. Minimum 1/4, 3/4, half, 3/4 and half inch. So these 3 nozzles are available. This you have to select depending upon the what velocity you got inside your stack. Higher the velocity, lower diameter of nozzle you have to take, so that your isokinetic flow rate will come within the range of metering device. Metering device here is this rotameter. There are 2 rotameters. So one is from 50, 0 to 30 LPM. So the 0 to 30 LPM is for PM, for setting the flow rate for PM. Other one is 0 to 6 LPM. So you can set a flow rate for gaseous sampling like SO2, ammonia, fluoride, something like that. So 1 or 2 LPM you can set here. And how you will set, how you will assemble the train, let us assemble the train. इधर ही बता देते हैं. Let them assemble how to place the impingers, where to put the probe pipe, where to put the pump for suction. So let them connect all the connections, so it will become easy to understand, right, sir? So in all this exercise, leak is very important, leak check, because there are many chances of leakages. So whatever connections where pull-push type connections are there is not much issue. For delta P, there is not much issue, because in delta P there is no suction or that sort of, there is only a pressure of the stack gas only. But when you are drawing a sample, in that we call sampling train. So from the nozzle, starting from the nozzle, then thimble holder. This is the thimble holder. So that thimble is a glass fiber or cellulose filter paper that is shaped in a cylindrical shape. Thimble hai na? No. So that, yeah. So ऊपर करके दिखा दो. So this is the thimble. इसको खोलो. So this is a glass fiber thimble. Glass fiber thimble, this is suitable up to 250 degrees centigrade. But if temperature is below 100, you can use a cellulose thimble. So likewise, you have to tighten it and then put it inside the thimble holder, like this. And then there are O-rings at each threading point. Wherever there is a joint, there are O-rings. One has to take care, put the nozzle. So he is putting one of the nozzle. Watch that O-ring is at its place. Otherwise, there will be a leakage. To avoid any leakage, you have to replace if any O-ring is damaged. And this is the probe pipe. This is only a 2-foot probe pipe. These probe pipes are available of different lengths: 1 meter, 2 meter, 3 meter, and then extensions. Up to 5 meters, you can get in extensions. Likewise, you see there is a handle at the end. That handle, what is the use of that handle? This. When you are doing sampling, this nozzle has to face the flow of the chimney, flow of the stack. But when this nozzle and thimble holder goes inside the chimney, you do not know whether it is facing the flow or not. So at the outside, you make the direction similar, and then maintain the position of the handle. With the position of handle, you will come to know my thimble is now facing the flow. This is probe pipe. This is hose pipe. Hose pipe is connected to there is a vacuum written here to this. And there is another terminal. Here pump is written. I will connect the pump with another hose pipe to that terminal. After connecting all this, what I will do? We will switch on the pump while doing the leak check, one should never put any liquid in the impingers. Otherwise, what will happen? When you will remove the thumb, because of sudden, there is a pressure drop, maximum pressure drop, and sudden release of pressure, entire liquid will enter into the piping, and that may go into the panel also. So, assemble the entire train. Do not put any liquid for gaseous sampling or for moisture measurement. Switch on this. Close this nozzle with the thumb like this, firmly. This is the PM rotameter. So there is a small ball. We call it float. So initially when you will switch on the pump, this float will go at the top because it is running at the full flow rate. When you will block the nozzle, it will start come down and finally it will set at the bottom. If it is setting at the bottom, it means there is no leakage inside the system. So this leak check is to be done initially. Then after setting all this, after deciding the traverse points, after deciding the duration of sampling, then a person will be standing for half an hour, 1 hour or 45 minutes to do the sampling at different traverse points at the specified flow rates. So this is all about the sampling of PM. If one is interested in doing gases like SO2 and other gases, impingers are fitted at the back side. So what is there? The air which is coming from the hose pipe here, that is then bifurcated. One part is going to the gaseous rotameter, and which is going to the gaseous rotameter. Before that, that is passed through these two impingers for gaseous, and the remaining part, because for gaseous you have to take a very small amount of volume. From say for example, it is 40 or 45 LPM flow rate for PM, and there you have to take only one LPM or 2 LPM. So balance will pass through this. At its place, there is a provision for putting bigger impinger. Here it is not available right now, but here the impinger is of bigger size, 250 ml. What for that is? That is for putting the chilled water in this ice box. You have to put the ice. So while doing moisture measurement, that will pass through at that time you will not be doing gaseous. Gaseous when you will be doing, when everything is set, when you have set the flow rate for PM sampling, and then you have started the 1 LPM for SO2 also. Because entire volume is coming through the filtration device or thimble, and we are bifurcating it there, and we are measuring at two places. So at the end, at the total volume, we have to add the two volumes. That we have to take care. We have to add the two volumes which we are measuring at 2 rotameters, because total volume is coming from the thimble. So I think this is all.
Yes.
Yeah.
Yes. Thank you very much. So what he didn't tell you that you can also use to measure beer or whiskey. You would like to take your choice. So anyway, this PM session is over. We have tea, and after that we'll come back very quickly. Just 2 smaller sessions, and then we'll have feedback and assessment. So today we'll finish little late, but let's finish it. At the end you will get the certificate. Not today. Certificate will be done. Tea is outside.
this afternoon a real quick rundown on gaseous Cems calibrations and some items that you may want to look out for in your own systems. There we go. Okay, calibrations. Daily calibrations of all monitors are required for ongoing quality assurance. The test must be conducted while the unit is combusting fuel unless a successful offline calibration demonstration has been conducted, and that's under Part 75. As we discussed, as I touched on yesterday, Part 60, which is another set of rules that govern Cems, you actually can have offline calibrations. So, but under Part 75, you have to be combusting fuel unless you opt for the offline calibration, in which you can use the offline calibration to validate data on a limited basis, up to 26 consecutive operating hours at a time. Typically, they are used for combustion, offline calibrations are used for combustion turbines that start up and shut down frequently, or what we refer to as peaking units. Gas monitors are calibrated using cylinder gases of a known concentration. And flow monitors are generally calibrated using electronic input signals. So calibration error and calibration drift. So calibration error is the difference between the concentration indicated by the Cems and the known concentration generated by a calibration source when the entire Cems is challenged. The CE test, or calibration error, is performed to document the accuracy and linearity of the Cems over the entire measurement range. In other words, we use a 0 and a span, the high span. Calibration drift is the difference in the Cems output readings from the established reference value after a stated period of operation, which no unscheduled maintenance, repair, or adjustment took place. Calibration equipment. Traditionally, we have the Cems shelter shown here, for example, is at the base of the stack or relatively close to the Cems, but they are remote. The cylinders are located remotely at usually grade level. So using high quality non-reactive materials are used for transport of sample and calibration gases. So you can either use like a stainless steel in some cases, or we can use Teflon or other variations of Teflon tubing. But the key there is to be non-reactive and non-permeable. Stainless steel or specialized non-reactive materials are used for calibration gas regulators. So depending on the gas type, you may need to use something outside of stainless steel. They can be coated with a glass coating or something like that, so it's not reactive, so you don't have loss at the regulator. So it doesn't affect the gas concentration that's being measured. Gases must be certified under the EPA protocol gas verification program. All calibration gases except for zero gas must have NIST traceability. Protocol gas verification program and the EPA protocol gases must be obtained from a gas manufacturer participating in the PGVP program. The EPA maintains a list of gas manufacturers participating in the PGVP program on its website. Protocol gases must be prepared according to EPA document 600-R or /R-12, 531, May 2012. EPA traceability protocol for assay of certification and gaseous calibration standards. Gas vendors are subject to periodic blind audits, and results are posted to the EPA's website. And you can see the link there. Calibration gases can and often are combined or blended with compatible constituents that are non-reactive with each other. So this saves you the number of bottles. So you can use multiple gases in a single bottle. You can have different calibration points for multiple instruments, as long as they don't react with each other. Calibration blended gases are analyzed and certified according to the PGVP program. And this technique allows for multiple calibrations while flowing gas from a single cylinder. This picture shows kind of a general calibration gas shelter that we have attached to a Cems shelter, and the regulators are protected, and we have pressure monitoring that is sent to the data logger that can actually alarm the operator if we run low on a gas. Calibration gases are delivered through the entire system to the sample probe as close to the tip as possible. It is important that the calibration gases are delivered at a similar pressure and rate to that of the sample system. So we want to make sure that you're within a very close tolerance so you do not pressurize the entire sampling system, which can cause an error in your readings. Clean and dry calibration tubing minimizes the potential bias of the system, especially when calibrating with reactive gases such as SO2. So as Roland was saying earlier about cold spots, you also want to make sure that you don't have any exposed cold spots on your calibration lines either. While they are not necessarily heated to the same temperature as a sample line, they are subject to cold weather. So if they're a well-constructed umbilical, we'll make sure that that is protected, and so you don't get cold spots there and condensation. Daily calibration specifications. Daily calibration using a zero gas and either a mid or high calibration gas. The calibration error cannot exceed 5% of the span value for the pollutant gas, or 1% CO2 or O2, which are the diluents. If the calibration error gets to 2.5% or 0.5% CO2 or O2, this is known as a maintenance limit. So in our data acquisition systems, when we reach this point, this sends a flag to the operator that lets them know that some maintenance needs to be done to the system, because now we are seeing a higher error. Alternatively, if the span value for the NOx and SO2 is less than or equal to 50 ppm and the result does not exceed 5 ppm absolute, or 10 ppm for spans of greater than 50 but less than or equal to 200 ppm, those are acceptable limits and they are passing. If the daily calibration does not meet these criteria, then the system is considered out of control and your data is now invalid until you get it corrected. Flow monitoring systems cannot exceed 6% of the span value, or 0.02 inches of water column. And opacity monitors must not exceed 6% opacity difference. The calibration process. Calibrations are conducted in a hands-off manner, meaning no adjustments are made to the system during the calibration period. So it is an as found. You don't go in and make any changes prior to the calibration. You run the calibration. If the calibration fails, then you can address that at that time. Calibrations are conducted within 8 hours of the unit's startup. That gives you an opportunity to get the unit lined out and out of startup mode and stable. Calibrations are controlled by the data acquisition and handling system in a lot of cases. So they will be set up to be triggered in a sequence at a similar time frame or in a given period of time. The data logger is also programmed with a sequence programming to activate a calibration when certain conditions occur, such as unit startup. So once the data acquisition system sees the trigger for fire in the boiler, then that starts a timer, and then within the 8-hour period, it will execute the calibration. The data logger can also be programmed to perform calibrations on a routine clock basis. So if we want it to be every morning at, say, 4 o'clock in the morning, which allows you to operate or run your calibration, and then if you have an issue, you can line that up with when your first shift comes online and they can address the problem rather quickly. If the parameters are exceeded, the criteria for passing, the data logger will flag the data appropriately, which provides an alarm for the parameter to the control room. Therefore, they can notify the instrument technician or whoever is responsible for managing the Cems, and they can take corrective actions. If the calibration fails, then the unit is considered out of control and maintenance is performed as soon as possible to minimize the invalid data period. Have been completed, a hands-off calibration must be performed to return to normal operation and have valid data. So this is kind of a key point there. So you conduct your maintenance activities, return the system back to service, and then you have to run another calibration. In some cases where the instrument repairs include the replacement of critical part or the sampling system, such as an orifice in an extractive dilution system, certain QA procedures need to be performed in addition to just a calibration to bring it back online and be valid. So this is an example of one chart that we use to understand what corrective actions might trigger what activities as far as recertification in the context of calibrations versus if you have to redo your cycle time response, analyzer replacement. If you replace the source in an SO2 analyzer, for example, what does that trigger? And so we have recommended corrective actions and then the following process for the procedure to get it back up and valid. This is sent to most of our facilities have a copy of this and they can look that up online. So for example, if you replace the Cems probe, you are required to do a linearity and a cycle time response. So calibrations are important. Calibrations are not just a formality, even though they may seem like very routine and just something that you have to do because they're telling us to do that, but that's not, it's actually a very valuable tool. Calibrations are your most valued instrument to troubleshoot problems. They give you a good indicator of what trends you are looking at as far as your instruments, drifting, and general maintenance. Routine maintenance is essential. For example, you have your sampling system, you have your sample lines, and while they are non-reactive and they might be of some really expensive material and you think that they're clean because they've been closed off and nobody's gotten inside there, that does not mean you don't get buildup from acid gases and other things in there. So it's highly recommended, for example, that you flush those lines out on a periodic basis, such as annually, to make sure that there's nothing in there that can influence your sampling system and also your calibrations. The problems that you can typically see in a calibration or as a result of a calibration can be very subtle and difficult to locate. The environment these systems are operating in are hostile, but the gases that you're sending up through these systems are also very caustic or acidic. So you can have the material that builds up in there can also have a safety impact, especially with very high concentrations of acid gases. Even calibration system components fail, such as tubing ages. You have, once again, Teflon. You think it's going to last forever, but it does dry out, get brittle. It eventually can crack. And also, if you are removing it and reconnecting it over time, your compression fittings can also damage the tubing wall. Regulator and wetted surfaces, they do corrode. Just because you're using a dry calibration gas, the acid in that gas can build up over time, and you can have on the diaphragm plates, you can have springs also that are in the regulator can become corroded. So you do need to do maintenance on your regulators. They are expensive, and rebuild kits are cheap, but you need to make sure that you maintain those properly. Compression fittings leak, as I previously mentioned, and they can also cause leaks by compressing on the wall of the tubing. It's amazing how many times you can find just a little crack that is developed from just removing it. Heated lines, pump heads, and peristaltic tubing, those are also prime targets for maintenance. If you're using an extractive system where you have moisture removal, you're going to have a peristaltic pump, more than likely, that's pulling the water out of the impinger and sending that to a drain or a container. You need to routinely check that tubing because it also wears and can leak, cause leaks. Pump heads also need to be changed routinely because they are a moving part, and the Teflon head can crack and cause leaks there as well. So that concludes my presentation on calibrations and some of the finer points there. Do you have any questions? All right. Which? NIST is the National Institute of that provides us with SRMs, standard reference materials. So they provide the materials to standardized materials to gas vendors to use as standards in analyzing your gases. Anyone else? Okay, thank you.
So let's come to the last portion. It's the fun unit, the fun portion. Mercury monitoring, something we didn't even know about 10 years ago or so. Mercury? What is mercury? Where is mercury? Something new. Something new to learn. And let's look into it. What is so special? There are things which are very special about mercury. and mercury monitoring. Let's look into that one. Okay, this one we knew. We have seen that already. Now we look for this little tiny thing here, Hg, or total mercury. What is so special about mercury? Mercury, it's the only metal which is liquid, in a liquid form at room temperature. All other metals are solid, very hard at room temperature. Mercury is the only one which is liquid at room temperature and therefore has a relatively high vapor pressure. Meaning, if I have a piece of steel here, I have no iron molecules in the air. Yes, I mean, 1 or 2. But if I have a bottle of mercury here, at 0 degrees, I have 15 milligrams per cubic meter. That's my saturation concentration. That is what I get, what I can get on mercury. So I have a very low melting point. It's a very heavy metal, molecular weight or atomic weight of 200. It is not water soluble, and the mercury compounds, primarily mercury 1 and mercury 2 compounds, they are all water soluble. And the very last part is very important. It's toxic, it's extremely toxic, and unfortunately our human body, or any bodies, but for us it's the human body which is the important one, is bioaccumulative to mercury, meaning I breathe in 100 mercuries and I breathe out maybe only 20 or 30. The rest stays in here. And that over lifetime means we're getting slightly more and more poisoned. And that's the next thing with mercury. Mercury poisoning is not, you get it, dead. No, it's a very slow process. So sometimes over many years. Total mercury, the regulation says total mercury. What is total mercury? That's the sum of all mercury, of elemental mercury and the mercury compounds. Where does it come from? Where does mercury come from in our environment? From waste, batteries, paint pigments, light bulbs, thermometers, seed dressing. One thing what a lot of people forget, that seeds sometimes are dressed as fungicide with mercury compounds, preservative agents, and many more things like that. In the water, wastewater, very, very big portion of the mercury in the wastewater and then in the wastewater sludge are the dental fillings. How do they get there? Go to the dentist, he drills out, and then he says, wash out, spit out. That's the mercury what goes into the wastewater, and it ends up in the wastewater sludge. And if you now take the wastewater sludge and put it on the fields as a fertilizer, you fertilize with mercury. Or if you burn it, what is done as alternative fuel in coal-fired power plants, replacing primary fuel with 5 to 10% of mercury sludge, of wastewater sludge, sorry, you add a lot of mercury to your coal emission, power plant emission. And then it's in natural gas, it's in heavy oil, and it's in coal oil. primarily in the so-called salt coal. What is salt coal? Salt coal, unfortunately, salt coal is the prime Indian coal. Salt coal coal is, I sometimes when I'm talking to very green people and they argue too badly about coal-fired power plants, I said, where is your problem? Coal is biomass. And it is, yes, okay, a little bit older biomass. But these plants were growing at the seashores, and that was the prime area where the Indian coal was coming from. Plants at the seashore, so seawater contains mercury. Organic material is mercury accumulative, so these plants accumulate mercury, then they become coal. The mercury is still in the coal, and it's also a salty coal, so sodium chloride from the seawater, that's why it's called salt coal, and that coal contains more mercury than coal which is coming from plants which grew just on dry land, because we're not exposed to seawater. And unfortunately, as I said, a lot of the Indian coals are salt coals. What is so special about the mercury monitoring? We're measuring a combination of elemental and compounds, but the second part is even more important. We're 4 to 5 orders of magnitude lower than any other pollutant what we are monitoring. If we monitor that low concentrations in the micrograms per cubic meters, not in the milligrams per cubic meters, our instruments need to be much more sensitive. And it's much more difficult to monitor that. So that is the next part. How do we do that? Total mercury monitoring. So, one, there is elemental mercury monitoring in situ with light transmission, external, but we're not interested in that one because that's not the regulation. The regulation says total mercury monitoring. Total mercury monitoring is either online, extractive, wet chemistry converters, or thermocatalytic converters. What does the converter do? It converts mercury 1 and mercury 2 compounds into elemental mercury, because the cold vapor atomic absorption spectrometer can only measure elemental mercury. Or offline sorbent trap methodology. We'll come to that separately. Then there is the so-called speciation monitoring. Speciation monitoring is one thing what India prefers. Speciation monitoring, again, offline or online. In the speciation monitor, I'm able to determine elemental mercury and ionic mercury separately. So I can get a reading for elemental mercury, and I can get a reading for ionic mercury separately. Is it important? It's interesting for the process, and it's interesting for my abilities to influence my combustion process. So to some extent it's of interest. To some extent, when I look into purely environmental issues, it's not that important. Okay, online in situ monitoring, as I said, for example, a DOAS, but this is only elemental mercury, it does not measure the mercury compounds, so that is not following the regulation. Offline extractive, This is one example where there is a sample probe, and then there is a combination of the detector and the converter, ionic to elemental mercury converter, and a calibration possibility built in so that the entire system, and you see that. I mean, we've seen this morning Cems cabinets. A Cems cabinet for SOx, NOx, CO is about this size. Mercury alone is this size. So that again shows it is a more difficult way of monitoring. Other possibility, other manufacturer has the system built in like this, has the reactor, thermocatalytic reactor, completely separated from the cold vapor atomic absorption using a different principle of monitoring, and faces some interferences and gets rid of these interferences. What is in that thermocatalytic converter happening? And that doesn't matter what manufacturer. They all work plus minus on the exactly same principle. There is stack gas coming. Stack gas contains SO2. SO2, you see, it doesn't go through to the detector. The same HCl doesn't go through to the detector. Keep that in mind. We're coming to that, why that is important. Then ionic mercury goes through and becomes elemental mercury. Elemental mercury is not affected at all by the converter, so it goes straight through. So this is trapped in the converter. This is transformed into elemental mercury, and this goes straight through. Now here I have my elemental mercury from ionic and my elemental mercury from elemental as a sum, total mercury, what I can measure, what goes to the detector. So a little bit chemistry. I mean, I'm a chemical engineer, so we have to do a little bit chemistry. So take the example of mercury chloride. I need carbon monoxide. I have a metal hydroxide as my converter material. Which metal is used is proprietary for each manufacturer. I have some ways to do that and know that, but I don't want to tell it. So with temperature, I'm getting elemental mercury, metal chloride, carbon dioxide, and water also evaporating. So this means I have a chemical reaction going in one direction, and because some of my components which are produced are evaporated out of the material, it's not reversible. So it can only go in one direction. And typically that goes more or less for all manufacturers. There is a typical lifetime of around 6 to 12 months for the lifetime of the converter material. I said SO2 is trapped. And I said, keep that in mind. Why is it important? 254 nanometers, that's my mercury peak in the UV. But there is a very big SO2 peak right there. And if my SO2 concentration is high enough, and here this is, for example, a 10 milligram per cubic meter SO2 concentration. If that is higher, that overlaps completely my mercury peak. So I have to get rid of the SO2, otherwise I can't measure my mercury. That is why it's important to do that and to to make that provision. In this case, manufacturer does it with a dual measuring and reference cell. Sample gas comes in, goes through. I have my UV lamp and 254 nanometers. Everything, SO2, mercury, whatever else, absorbs 254 nanometer UV light. Then my sample gas goes through a mercury trap. And this is an activated charcoal which absorbs exclusively mercury. And then it goes through the reference cell. So in the reference cell, there is no mercury. I have my measuring signal, here the reference signal, the difference is my mercury signal. A calibration of mercury, again, like with dust monitoring, no bottles, 10-liter bottles, compressed mercury calibration gas. So you have to produce your mercury calibration gas at site in the instruments, so that on the first example, the calibrator was included. Second example, it's a separate unit. The calibrator can either be a wet chemical production of calibration gas, where you have a mercury standard, liquid mercury standard, typically mercury nitrate, with a certain concentration. You have a peristaltic pump with a defined flow rate, calibratable defined flow rate, and you push a certain amount of mercury, liquid mercury, into a stannum chloride solution. Stannum chloride is heavily reducing and immediately reacting with the ionic mercury to form elemental mercury. Elemental mercury is not water soluble, so with zero gas it's purged out and I produce my calibration gas. And based on the concentration of my mercury in here and the flow rate of my sample pump and the flow rate of my zero gas, I can exactly define what is my concentration to check, not calibrate, but check my analyzer, spin check my analyzer. And if I switch that off and keep everything else running, that's my 0 point. Other possibility is that this mercury solution, what I said, mercury nitrate solution, with a peristaltic pump is directly, and through a vaporizer, is directly included into the analyzer or into the sample probe, and in the vaporizer vaporized, and then with the sample gas transported to the analyzer, or in the same way, and this way calibrating the entire sample gas or the entire system, including the heated sample line. On mercury, again, remember what I said this morning, sample handling systems, no cold spots, very, very important on mercury, that there are no cold spots, because any cold spot will create a condensation of mercury or mercury compounds, and we will have false measurements. Now, when we come to sorbent traps, I'll give over to Steve. You want that? Yes. Okay. Just a sec.
Test, great. Before we get on to our last topic of sorbent traps, just a couple items to add to Roland's presentation, a couple lessons learned from mercury monitoring using mercury Cems in the United States. The mercury Cems that are used in the United States are overwhelmingly based upon atomic fluorescence, very good sensitivity with those devices. The main provider is Thermoelectron with their Mercury Freedom device. I understand that they are a player in this market. At least in the United States, those are dilution-based systems. And in theory, you could use instrument air for dilution, but that will significantly affect the sensitivity of your analyzer. And the issue is that oxygen will quench the atomic fluorescence, which is what you're actually trying to measure. So you want to, if you're using a dilution system with an atomic fluorescence, use a nitrogen generator to provide your dilution gas, and that will give you better sensitivity. Moving on to sorbent trap monitoring systems. Under the mercury and air toxics rule, all coal-fired sources are required to monitor mercury. About half of those sources, roughly, use a mercury Cems, again, overwhelmingly atomic fluorescence-based. The other half use sorbent trap systems. Now, a sorbent trap systems is just a simple manual method that makes a time-integrated mercury measurement. There are procedures both in the European standards, 17286, or the US EPA performance specification of 12B that can be used for sorbent trap systems. And under the MATS rule, you can use sorbent traps to measure the mercury in your flue gas for up to 15 days at a time. The equipment, we have an example there on the screen, consists of the following. We have a pair of 3-section carbon sorbent traps that we use, 2 of them. For each of those traps, you have a sampling system, very much like was illustrated previously, where you have a probe with 2 traps at the end, vacuum pumps for each, heated sample lines for each, a dry gas meter or a mass flow meter for each of those, and then moisture removal components. So we're drying the gas, taking out all the moisture before we measure that gas flow. And then temperature and pressure sensors associated with each system. The analysis of those traps can be done either on site by the source or by an outside lab. Typically, overwhelmingly, that is done by thermal desorption, and then that is measured using an atomic absorption analyzer. So how does it work? Very simply, the sorbent media collects the mercury while we're measuring the sample that's being pulled through each of those traps with the dry gas meter. The concentration simply will equal the mass of the mercury collected in that sorbent material divided by the volume. And you see an example of the probe here. Again, we have 2 sorbent traps. You can see the end of them sticking out here. If we look inside, you can see the 3-section traps, and I'll talk about what each of those sections represent. And then for each of those traps, we have water knockout, we have dry gas meters, everything associated with trying to measure the volume of the gas. Again, 2 sorbent traps are involved. Each of these sorbent traps, when they're used for continuous sampling, have 3 sections. In the first section, that is the primary capture section. We expect nearly all of the mercury to be captured in that first section. A second section is used to assess whether that collection is getting done. If there is significant amount of mercury that's collected in that second section, something's wrong. We should have collected overwhelmingly the mercury in the first section. And then there is a third section which is used for QA. It is spiked with a known concentration of mercury, and this will assess our technique, whether we're losing some for some reason, or the technique of the person who's analyzing the traps. Do they get the number that we expect them to? Under Performance Specification 12B, we're required to do leak checks like we would for a Method 5 train or a Method 17 train. And we are required to ensure that we are proportionally sampling. With thermal power plants and other sources within the United States, they're already required to measure the volumetric flow rate at their stack. So they simply use the Cems data for that. However, as illustrated in these graphics, an S-type pitot tube could be integrated with the probe, and that could be used to ensure that the sampling is being done proportionally. There are also other QA/QC that are required. We're assessing the spike recovery. We're measuring from 2 traps so that we can compare the results and make sure that they match up as we would expect them to. We're assessing the breakthrough, as I've already measured, and we have QA criteria for each of those. So it's very much a method where the proof is in the pudding, if you will. In addition, under PS 12B, we are required to do an annual RADA, as well as doing quarterly QA of the sampling hardware. So we have to calibrate and check the sample flow meters and the temperature and pressure sensors. If it meets all the requirements, then we simply use the average concentration, again, mass divided by volume, for both of the traps. And there are some options in 12B if one of them meets it, or if we don't pass the relative deviation specifications. Now, some recommendations. I'd certainly suggest that for sources, sorbent traps may be a very good option. For sources that have compliance margin, that is, they're under the limit, but these could be somewhat problematic for sources that are operating near the limit because there's a delay in getting the results. You have 15 days, usually these are operated for a week at power plants in the United States, but if you're not doing that sampling on site, if you're sending it off to a lab, there may be another week where you're waiting to get the results. So you have to operate your unit in such a way that you maintain enough margin to make up for that time delay. And that may mean controlling your unit more tightly than you would have otherwise, injecting additional carbon or some other method of control more rigorously than you would otherwise, and the cost associated with that. Also, when you're choosing between sorbent traps and mercury Cems, you may want to consider stack access, because obviously you're going to have to come up and down the stack, probably weekly at least, to change out the traps, and the total operating and maintenance costs associated with the system. For regulators, a couple of suggestions. The EU, their criteria only identifies what we used to know of as the Ontario Hydro method. It's a wet chemistry method, 13211, as the only reference method for mercury that uses potassium permanganate and sulfuric acid. Again, it's a wet chemistry method, but in the US, we use method 30B. And with method 30B, we're using a similar trap, a two-section trap. And I found an antique here recently when I was cleaning out some of our corporate storage. This was a very early version of essentially a method 30B trap. They don't make them like this anymore, and for a good reason. One of the things that we did find in evaluating these traps very early on is, there's not much space between the inlet of this trap and the first section, and they're divided by little glass wools so you can analyze each section separately. We found that we needed some additional room in order to ensure that in the heated probe, we vaporized any condensed liquid so that it didn't cause us problems with that water entering the sections. Now, method 30B is based on using two section sorbent traps sort of as a vestige of how this method was initially developed. One thing I would say is sorbent traps certainly have proven to be reliable as an accurate SRM, but I would recommend that a better option would be to allow a variant of method 30B using a three-section trap, because with a two-section trap, what's done for 30B is some of the traps are spiked and you calculate the difference based on the results of the other. So you're going to do a much more accurate measurement if you use a third section for that spike independently. Finally, there is a requirement to maintain flow proportionality, as I've discussed. Both the US standard, method 12B, as well as the European standard that was copied essentially from method 12B, require you to assess whether or not you have flow proportionality based on the first hour of sampling. That first hour is probably the worst one to pick because you're bringing the pumps up to speed. You may be coming online. A much better approach would be to use the average of the entire period and then assess each individual average against that total average to make sure that you're proportionally sampling for the entire period. And I would suggest that it makes sense to include the US option of assessing whether or not you pass flow proportionality with the allowance for a few hours of deviation, especially given situations where the load might be changing. Thank you. Are there any questions for myself or Roland regarding mercury monitoring? Did you hear that?
Sir, in the slide, that catalytic converter reaction is given as bidirectional. Metallic hydroxide, some reaction is given as that slide. Previous
Sorry, I
slide.
didn't catch that.
In your presentation, sir, for trapping, catching mercury, you have given one chemical reaction, no, sir. Metallic hydroxide.
It's not continuous monitoring, right. But it is continuously sampling, so it's representative for that entire period.
No, sir, that old one, SAR told, no, sir, the Ronald Stark presentation.
What?
Sir, in your presentation,
Yes.
that metallic hydroxide reaction you have given, sir.
Yes.
And that is given as a bidirectional reaction.
Yes. Thanks. Let me just go back. Yeah, thermocatalytic converter.
Yes, sir.
Here.
That reaction symbol is showing as bidirectional.
So
I'm confused.
metal hydroxide and metal hydroxide reacts with the HCl and the electrons coming from the
That I understood, sir. That symbol between the first reaction, second bidirectional, vice versa it is going.
Okay. Oh yeah, forget this. That's why I specifically mentioned it can go only in one direction.
Okay.
Yes, you caught my error. Thank you. No, it is not, it's absolutely not bidirectional. It's not possible. Any more questions?
Where's the CO coming from?
The CO is coming from the flue gas. Yes, yes. This is my combination in the flue gas here.
The temperature and pressure conditions for the heated lines above the boiling point of mercury?
Yeah, the temperature and pressure situation I only need when I do my normalization of my measurement. But here, the temperatures are always, I mean, we're talking about, remember, on one of the first pages, I said 15 milligrams per cubic meter. 15 milligrams per cubic meter is the saturation concentration of mercury at 0 degrees. But what are we measuring? 10, 20, 30 micrograms per cubic meter. Factor 1,000 lower. So we will not lose anything. Even if we go through I mean, every analyzer, you have seen the two examples for the extractive analyzers. Both have sample gas coolers in there. Sample gas cooler will operate at 2 or 3 centigrades. It will not take out elemental mercury because the concentration is way, way below the saturation.
Okay, thank you.
Any more questions?
Sir, is there any disposable procedure for industrial mercury? Means your electrical component like relays will have a mercury weighted relays. Any disposable procedure, means CPCB will say, or any guidelines for disposing mercury scrap? Mercury scrap.
Guidelines for disposing mercury?
Batteries we are disposing, handing over, no sir, for lead and all. Like that for mercury, any disposable procedure is there? Dispose. Recycling or waste management.
It is hazardous waste.
Yes, how to dispose it?
And needs to be disposed as if I, let's say I run my plant. I have a mercury control, meaning I use charcoal, activated charcoal to trap mercury, to absorb mercury. When I take that out, this is hazardous waste.
Yes, sir.
It has to be disposed as hazardous waste. Of course, I can throw it into my boiler again and burn it, but then I keep on cycling my mercury.
There is no separate Cems process for mercury disposal. That falls under that.
Any more questions? No more questions.
Thank
We
you.
don't answer any questions which are in your papers, okay? Thank you.
Finally, it is going over. I'm not supposed to give the answer here. I'm just going to discuss the question. And I'm not going to test. You will self-evaluate yourself. You are good enough to do that, so I'm not going to evaluate you. And if you see the seat, the first thing which comes is this. Please do write your name clearly. That will be on your certificate, and your email very clearly, where you will get the certificate and other documents, presentation, etc. So if I can't read it, you can't get it. And after that, I would suggest the last page, if you see, there's a feedback sheet I have already individually conveyed to you. The feedback sheet in the last has 4 points where you can evaluate, be good, bad, justify, reasonable, or whichever way you want to give that feedback. And there's a separate feedback, general questions for industry. Industry people can do that. For regulators, regulator people can do that, fill that in table as briefly as possible. And other researchers and other people can do on the last one table. So all the tables are not required to be filled, but wherever it is applicable, you can fill that. Meanwhile, all these questions, so you missed that? Okay, there are seats left. So all the questions are very simple. These questions come from the main points that was given in the slides. Our presenter has repeated to you at least 3-4 times. That was the question, and it is also from the guidelines. You are also free to refer the documents, whichever you want, it is open. And I didn't give you the presentation in the beginning. The only purpose was that you will listen carefully what it is saying, and all those things are supposed to be explained 3-4 times. These are easy things. But the purpose behind it is you got those points which we wanted to highlight. That is, I'm just going to read the question, and you will be able to evaluate what will be your answer. And at the end, we will be genuinely evaluating ourselves. So the first question, Cems is an automated device for air emission monitoring in the stack and generate data on real-time basis. I don't know what the answer is, but I think you know it, right? How many knows this answer? Which one is not knowing? Sir, how many knows the first answer of the first one? Okay, then you wrote the answer. I'm not going to tell it again. Cems is used for monitoring of gaseous emissions and ambient air quality. I'm talking about Cems. And the data is sent to the regulator. How many agree to this? You agree with this? Cems is used for ambient air quality? Now you got the answer. I'm not giving the answer. Quality assurance of Cems is important for ensuring credibility and accuracy of the emission monitoring. In the European Union, it is carried by type approval or the certification process, we call it. You know the answer. You can read my pitch of my voice up and down and figure out the answer also. Quality assurance of Cems is important for ensuring credibility and accuracy of emission monitoring. That is the 4th point. In the US, it is carried by type certification process. How many on yes? No? Wow. You got successful training. Number 5, Qual 3 and AST are quality control process for Cems in European Union. Performance test of Cems is mandatory for every installation of Cems in United States. Performance test of Cems. Performance test of Cems is mandatory in every installation of Cems in US. Now I'm in mute. Performance test in US. CPCB guidelines allows only certified Cems and not non-certified Cems. CPCP certified and provides the list of certificates, Cems equipment to be used. Which one is true for Cems calibration requirement in India? Point 9. During installation, 6 monthly upon major repair. During installation, every 3 monthly. 6 monthly upon major repair. During installation only. Which one is true? Number 10. For Cems data handling, CPCB requirement in India. Cems data handling, direct from Cems, two-way data connection, and transfer to CPCB and SPCB. Data through industry server to CPCB and SPCB. Data through intermediate vendor. If somebody is doing that, is not correct. Server to central, yes. 11. Which one is true for CPCB requirement of maintenance of Cems? Daily zero test, daily span test. Weekly zero drift and span test. Daily zero and fortnightly span. Yes. Selection of suitable Cems technology in case specific and depends, selection of suitable Cems technology is case specific, depends on operation type, stack structure, flue gas characteristic, among others. True and false. CPCB demands installation of mercury Cems in all coal-based thermal power plants. You remember the first chart I had shown, there are two categories, power plants, thermal power plants. What? Yes. So vendor may hate me, but that's the thing. Number 14. Which one will be the best suitable PM Cems technology for 660 megawatt power plant? Best suitable tech Cems for PM in 660 megawatt power plant with ESP and an emission limit of 30 milligram. 3-4 points is here. One, we are looking for PM Cems. It's a big plant, 17 categories, which is 660 megawatt. It has ESP installed. Emission limit is low, that is 30 milligram. Now you have to see which technology will be used. Forward scatter, opacity meter, triboelectric. Opacity monitor usually, that is very low concentration for opacity. It can monitor, but you are not very good for sure about the accuracy. Triboelectric may have some kind of disturbance if it is not right type. That is because of ESP also works on, it is not the only case, but ESP also works on electromagnetic field. Triboelectric works on the same formula. There will be many part of gaseous particles which may be resistive, which is not captured in ESP, but still it goes through that, and it will not react on triboelectric. There will be flow change, and flow change, because of that flow, that reading can be changed. So, which one is the best? A reading can be changed slightly, but here the concentration is 30 milligram, which is very low, so the equipment has to be very sensitive. Forward scatter, opacity meter, triboelectric, once again. You learned it. Which one will be the best suitable PM Cems technology for 660 megawatt power unit with ESP and FGD installed, weight FGD installed? Limit is 30 milligram. Opacity, extractive forward scatter, triboelectric. There could be multiple options, but I'm saying out of 3, so that vendor doesn't fight with me outside. Number 16, a power plant with weight FGD and SO2 norm of 100 milligram can install hot type extractive gaseous Cems monitor? I'm reading it again. Power plant, weight FGD. So flue gas condition is weight. SO2 norm is 100 milligram, which is the lowest for India at least. And if you install not hot type means what? Hot type means the entire gas sample tube is heated, so that gas inside or moisture inside remains in the vapor form. So it is not condensates the mercury, SO2 particle. Or if it is not hot, what will happen? There will be condensation. And your SO2 you will get, that will be dissolved into that. So we'll not be able to monitor. So again, which one? 17, sorbent trap is a technology used for? Excelled in the mercury training. Number 18, data monitored by Cems need to be corrected for oxygen, temperature, pressure. Let me complete. Somebody answered already. Okay, I'm moving next. Yes, that's true. 19th, PM Cems should be installed 500 millimeter below the gravimetric sampling port. 500 millimeter below. Why there should be a difference between PM monitor or Cems? So it should be manual monitor, Cems should be below or Cems should be up? Number 20, US EPA demands 4 quality assurance audits. There are 4 tests: RATA, linearity check, 7 days drift, and cycle time response. Which one should be conducted last to avoid having to repeat the test? They are expert now. Yes. And if you fail, what will happen if it is not done in the last? You have to redo all the tests. Successful training from US EPA. 21. What does the acronym RATA mean? 1, 2, 3, 4, which one? Number 22. What is the frequency to perform linearity quality assurance audit in the US? Semi-annually, annually, quarterly, or only as needed when calibration fails? What is that? I also have to see. I'm right, yeah. Yes. It was one of the main points in the slide. Number 23. Linearity check is carried using low, medium, and high gas concentration levels to assess the Cems response. What is the correct sequence? Which one? No same gas should be supplied in sequence. So which one? Why not first one? Low, medium, high, low, medium, high, low, medium, high. Why not this one? It is saying that, do you have that, give it to them. It's the right time you can explain again. Yes. So if any of all 3, yes, any of them is repeating one or other thing.
You cannot repeat the same gas twice. That has to be done separately. So you would want to have separation between, say, a high gas and the next gas cannot be the high gas again.
So that's what it said. Same gas should not be given repeatedly in sequence, one after one. So first one is the answer. I'm sorry, I tell this. 24. For cycle test, 0 and upscale calibration gases are injected to determine the upscale and downscale cycle of response time. You can also, you would like to explain, Sean, you can explain. 24. Which one is the answer? They know basically, yeah. 25. Why is monitoring of total HG different to monitoring of other gaseous pollutants. Monitoring of Hg is different from other gaseous monitoring. How? Okay, I'm moving next. As per CPCB guidelines, non-certified Cems required to undergo performance check, which should include calibration function, variability, data comparison with data quality objective, establishing calibration function with SRM. False. So somebody ignored the CPCB guideline. 27. US EPA certified Cems are mandatory to be used by industries in India. 28. The CPCB guidelines require 85% data availability to be ensured by industries. 29. Using remote calibration system, a regulator can check whether PM Cems is working properly or not. PM Cems. Last, proper implementation of Cems can help to optimize the operations, save resources, improving efficiency, beside credible pollution monitoring, reporting, and quick control in case of non-compliance incident. So there are 30 questions. How many of you got between 28 to 30? How many of you got 25 to 30? Be genuine in your self-evaluation. How many of you got between 20 to 25? How many below 20? Okay, so I believe those who had been below 20, they started taking quite before in advance, right? It appears easy, but there is a little bit of trick. Anyway, in that seat, just below that, assessment score you can do out of 30 how much you have done. You can sign it yourself. And please do write the feedback. Feedback, the first table, you have to score what is the satisfaction with the training material. Be genuine, whatever you want. Satisfaction with the workshop presenter. How well organized was the event. Overall satisfaction with the program. Out of 10, 10 is best, 1 is lowest. So do that. And there are 3 tables followed to it. General questions related to Cems. If you are industry representative, fill that one. If you are environmental regulators, fill the second one. And if you are researcher or anybody else, you can fill the third one. Please write, try to write readable format, and you can keep that thing here. We will submit all those details. We will verify the emails. We have following event in Delhi on 28th, 29th, which is identical. And if some of your colleagues or anybody you think is relevant for them, you can ask them to join in Delhi. We have space there right now, so I'll be happy to accommodate. And once both the programs are done, we'll send all those details, data. It will get approved, and all the emails we have, you will be sent all the presentation materials before you come one by one to ask me. So all these material will be sent to your email, but it will take 2 weeks. All maybe some photographs, all the presentations, maybe readable documents related to that, and the certificate. It will take some time, at least 2 weeks. And as soon as you finish, don't run away. One of the important things we are missing is a group photograph. We'll assemble here, we'll take a photograph together. So submit the paper here, maybe here on the seat, once you fill it, and then we'll have a photograph. I'll say you goodbye then.
అయిపోద్ది నేను తెచ్చాను బ్యాక్గ్రౌండ్
अरे आपका है ना चलो
हाँ रिकॉर्डिंग
इसी से होगा हमारे कैमरा से नहीं होने वाला इतना सवाल है
ओके ओके
और उसके बाद एक बड़ा जूम
हाँ
आई जस्ट सर आप भी चाहिए थोड़ा और पीछे जा सकते हैं इससे आ रहा है वो आ जाएगा सब आ जाएगा और पीछे 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 हाँ सब इफ somebody want to sit can sit come fast if you want they must come
एग्जाम पेपर लेंट बाहर आए
I'll take and then we'll go. Now, sir, camera पीछे करो. Anybody has more hi-fi camera phone? इसमें आएगा नहीं तो फिर क्या फायदा फोन कट कर दो मुझे लगा यू आस्क्ड मी टू पिक अप from this side okay
ఓకే సార్